So welcome to everyone. If you can go to your place, please, we're going to start. So in name of the DCO committee, I'm really pleased to welcome you all here in the amphitheatre in Cordeliers, and also I warmly welcome all the people who are following us through the video projection. Perhaps just on the chat, just explain if you can really hear us, if you can see us really, because of course it's not so easy to prepare such a conference in a hybrid mode, but we are really happy to have been able to do that. So we, of course, because of this mode, we are going to try to stay in time. So I'm also not, will be not so long, but it's really my pleasure to say that this conference is made possible with the collaboration of our colleagues from JOC, and I will let them the floor for a few minutes. And I also want to warmly acknowledge the financial support of the Société Chimique de France, Sorbonne University, and also our LABEX, MyChem and Charmat. Without them, it should not be possible to do such days. So the DCO committee is brand new, and we are very happy to have the possibility to prepare all these days. I'm going to be quite quick for the presentation, but I just wanted you to know the name of the people. You can also read what will be their specific task in the committee, and please, we are really there to help and to answer to questions. So here are the name of the people. You can see they come from Montpellier, come also from near in Paris. Here you will have a series of people from Paris. And we are here also together with some thematic groups who are with us to represent here for Mathieu, supramolecular chemistry. I have the pleasure to chair this committee. Anis comes from Lyon, and Boris is representing the group Chemobiologie, also in the DCO. So really, Sébastien is also with us. So please, you have the names. You have here also the link with a website which is really very practical and up to date. So don't hesitate to come to us if you have any questions. Why should you come to us? What is our mission? You know that, but I also want to introduce to the younger people what is the role of the Division de Chimie Organique of the SCF. So of course, our mission is really to support, inspire, stimulate the organic chemist community, not for the organic community alone, but also at its interface. It's, of course, really very important here. So we are organizing scientific events like that one. We support also some scientific events you want to organize, so don't hesitate to come to us for asking that. We try to have a wide and diverse communication with our small journal, but also with the social links and so on. So don't hesitate to have a look at that. And we also really want to promote the visibility of the DCO chemists through prizes. And we are very proud to have prizes from which were given by the preceding committee, who are going to speak today. We have also, we propose for distinguished members of the SCF, and also we help young such as to go abroad and meet other people from the ICBMS society. So of course, we have to work to have link with the scientific societies abroad. So please retain this message at your disposal to exchange and help. And we are able to do this hybrid manifestation today with the help of Annis, Leana Travaglini, who are editor-in-chief and deputy editor with ERJOC, our journal, our chemical journal, and I will, for the 2 minutes who comes, I will let the floor to Anne. Anne, I changed the slide, and please just say a word about the link between the DCO and ERJOC, please.
Thank you very much, Emmanuel, and also for giving me the opportunity to say a couple words here. And first of all, to all the speakers and all the attendees, a warm welcome to this year's or to the fall Journée DCO. And I'm also very happy that over the past few years we were able to collaborate on so many successful initiatives with the DCO. And here I would like to thank the DCO, and in particular Mathieu Solobou as the former president, and you, Emmanuel, as the current president, for making all of this happen. And in addition, I would also like to thank Philippe Dubon in the past, and now Olivier Bazelet for all of the efforts in this regard. So in addition to the scientific events that we've collaborated on, we are also collaborating on a special collection that highlights the winners of the DCO prizes. And for this, we invited all of the awardees to contribute an original research article or a review to EuroJoc. And I have to say, I'm very proud that for the 2020 winners, all contributed to this collection. And we have 5 actually excellent covers that highlight their work. So please check out this collection that you can find on our homepage under special collections and then society prize winners, as shown here on the slide. A nice editorial will also be published soon that is written by Mathieu, and this will then round off the 2020 collection. We've also continued the initiative in 2021 and invited all of the prize winners, and here also the response was great, and we already have the first paper online, so please also look out for that. And then just looking at the program, I'm happy that so many of the prize winners will speak today, and I look forward to everybody's talks and to a great day of science together with the DCO. And thank you again for this great collaboration.
We thank you very much, Anne. Mathieu is listening to you, and it's really a great collaboration, and we will really do our best to go further with this nice collaboration. We will speak about that at the end. Thank you so much, Anne. So now it's time for our scientific day. Here you have the program at a glance. So please, I really want to acknowledge all the speakers who accepted our invitation, and we will really have a great day with a lot of nice presentations. We have to take care about the time, so the speakers and the chair will try to do their best for that. Okay, so we will now begin, and I'm really pleased to welcome Jeanne CRASSOUS. So I will do a short presentation, and then of course Jeanne will deliver her lecture. So Jeanne completed her graduate studies at the ENS Lyon, where she was admitted to the aggregation de sciences physiques option chimie 92. She then prepared her PhD in Lyon under the supervision of Professor Henri on the absolute configuration of bromochlorofluoromethane in 96, and then she has done a postdoctoral stay with François Diederich in Zurich on chirality in Rennes. Jeanne was recruited in the CNRS in 98. She moved to the Institut de Sciences Chimiques de Rennes in 2005, where she became CNRS director in 2010. So she leads with Ludovic Favreau a group about organometallic chiroptical systems in Rennes, where she is specialist for the synthesis, characterization, but also applications of molecular-based materials on organometallic helicens, and also chiral organometallic complexes for fundamental chirality and chiroptics. Jeanne is the author of more than 130 publications in renowned journals, and she undoubtedly promotes French chemistry abroad. She has been invited to give more than 100 guest lectures, keynotes, and conferences in congresses, laboratories, and universities. Jeanne was named SFC Junior Distinguished Fellow in 2013. We are very honored to receive her for the opening of this meeting on the occasion of the DCO Award ceremony. Jeanne, the floor is yours.
Thank you very much, Emmanuel. And it's a very big honor and pleasure for me to be here today for this special day, and in person and hybrid day. So let's hope it will continue like that.
Je suis désolé.
Okay. So as Emmanuel said, during my CV, I want to dedicate this presentation to my two mentors, big professor chemistry, so Professor André Collet and Professor François Diedrich, who are very important for me and for my scientific career. I want also to thank the group where I am doing my research work, and especially Professor Régis Réau, where I came, in which group I came more than 50 years ago. And here you have all the names of the group, and I'm currently dealing with chirality aspect with Dr. Ludovic Favreau. I want also to thank my former colleagues from ENS Lyon, especially Jean-Pierre and Henri, and all my collaborators. As you will see, I have many collaborations, and most of them, the most important, are from Villetaneuse, Marseille, Buffalo, Krakow, and Durham. I want to, of course, to thank all the financial support, especially CNRS, who is giving me my salary since a lot of times now. And I, of course, want to thank all the students with whom I'm making everyday work, and without them, I wouldn't have a result at all. And of course, I would like to thank the Division de Chimie Organique from the French Chemical Society, so the former bureau who elected me for this very nice prize, and particularly my warmest thanks to Mathieu Solegou and to all the people who have contributed to this prize. So regarding what I'm doing in helicene chemistry, so first of all, what is a helicene? So helicene is formed of orthofused heteroaromatic rings. They have an extended helical pi conjugated system, and they are chiral. They have this helical shape. So you can have right-handed helix or left-handed helix, and they have strong chiroptical properties. So historically, the helicenes were done, especially the first example, which is typical, is the hexa-helicene. It was developed in the 50s through a very complicated multi-step synthetic pathway. So taking advantage of Friedel-Crafter cyclization, and the enantiomeric resolution of this chiral molecule was done using this famous TAPA derivative, which makes acid-base complex that you can resolve, the diester isomers you can dissolve by crystallization. But a more common synthetic pathway that we use every day in the lab is based on this photocyclization reaction of an olefin system, which can be obtained through a classical Wittig reaction. So this is the multiple elementary step of this photocyclization in the presence of an oxidant, and it's very convenient to access a great diversity of edicenic molecules. And very conveniently, through a very efficient collaboration with people in Carros Science in Marseille, so Nicolas Vanquin and formerly Christian Roussel, we are using chiral HPLC resolution, and we get the enantiomers, the pure enantiomers. So as I said, the LEHN are very interesting because they have strong optical properties. So for example, they have huge optical rotation. If you compare them to more classical molecules, so several thousand. They have also strong electronic circular dichroism with a very typical signature, as you can see. For those who don't know, the circular dichroism is a difference between the absorption coefficient between left-handed and right-handed circularly polarized light. And here it's a typical signature of a LEHN. So with a strong band here at 330 nanometers and at 250 nanometers. So you will see that is a typical fingerprint of LEHNs. And we typically define the symmetry factor, which is a ratio between the CD and the UV. Here, what also is interesting is another optical properties, which is called circularly polarized luminescence, is analog of circular dichroism, but in emission. So if a molecule is chiral and it emits light, then you will get a light which is circularly polarized, which means that you will have more than left-handed compared to right-handed emitted light. And typically you get a signal which is either positive for one enantiomer or negative for the other one. So for example, for the classical carbo-6 LEHN, you have the strong UV because it absorbs a lot. You have a typical signature in electronic CD, but you have also emission, fluorescence, and circularly polarized fluorescence. And typically the value is 10 to the minus 3. So for organic molecules, the value, typically the dissymmetry factor, which is I will explain you, sorry. So this is what we have in circular dichroism. So when you look at theoretically at the circular dichroism, you have the product of electric transition dipole moment and magnetic dipolar moment multiplied by the angle between the two moments. And in emission, you consider what we call the dissymmetry factor, which is the ratio between the emitted light, circularly polarized, and the total light. And this is the ratio between the magnetic and electric dipolar moment. So the higher this value, the better will be the molecule in circularly polarized emission. And in maximum will be +2 or -2. So I want to show you the main area in which LEHN chemistry is involved. I have chosen some research from the French community. So in Gypsy-Rivette, there are a nice example from Arnaud Voiturier and Angela Marinetti in catalysis. There are nice examples also from the groups in Marseille, Marc Gingras and Johan Coquerel in helical nanographenes. And also the group of Arad Bock and Fabien Durola are working on LEHN microcycles. And in our case, we are working on these organometallic LEHNs. And also some people here in the audience are working in LEHN chemistry. So what about the chemistry we are developing? For example, recently, we have developed the molecular engineering of LEHN, decorating this helical backbone with dicoetopyropyrrole, which are good chromophores, very strong chromophores, and they have a nice red or pink color. And as you can see here in the UV, you recognize the typical absorption from the LEHN part, and this is typical absorption from this dicoetopyropyrrole chromophores. And if you look at the electronic circular dichroism, you have the typical signature of the LEHN, and it appears new band here around 600 nanometers, which come from the presence of the chromophore. So you see you have a nice fingerprint in circular dichroism, which is quite strong. And if you magnify the fingerprint here, you have a typical positive and negative signature. And this typical positive and negative signature is called the exciton coupling chirality. And it's exactly this exciton coupling chirality which helps to increase the circular dichroism response. And on top of that, these molecules are emissive, they are chiral, so you make appear a very nice emission, circularly polarized emission, which is not bad for chiral organic molecule with a response about 10 to the minus 3. Another possibility to increase these characteristical properties are to graft some acceptor moieties. So you can graft on the helical backbone this naphthalimide acceptor compound, 1 or 2. And typically with this donor acceptor compound, you have nice fluorescence and you observe nice solvatochromism. And because of this solvatochromism, you have the opportunity to look at how the CPL, circularly polarized emission, is influenced by the polarity of the solvent. And so if you measure the circular polarized luminescence, you can see then from a less polar solvent to a more polar solvent, you decrease the CPL response. So this was actually the first example of studying how the symmetry and the polarity of the molecule influence the circularly polarized emission. And on top of that, so because this molecule displays quite a good CPL response, so it's around 210 to the minus 2, which is quite strong for organic molecules. We were able to incorporate this type of molecule into an OLED device, organic light emitting diode. So in collaboration with a group from the CEA in Grenoble. And we could get an OLED emitting a circularly polarized light. In parallel with our molecule, which we name platina LEHN, so an LEHN incorporating platinum, so a heavy metal with a strong spin orbit coupling, which enables to go to the phosphorescence. These compounds that we developed in the lab were incorporated by a group at Imperial College in OLEDs, and they were able to have an OLED which is emitting light and with quite a strongly circularly polarized light. It's a 0.44, so it means more than 20 or 30% more of one left-right compared to the right light. So there is a strong increase of the circularly polarized light, and in collaboration now with this group through a European project, we are trying to understand what is going on in this process and how we can improve even more the properties in OLED technology. So to go more into detail in the chemistry, so as I told you, we use this typical photocyclization reaction to construct a helical backbone. And then we use a classical organometallic chemistry, for example, this cycloplatination, to incorporate a metal into the helical backbone. So through enantiomeric resolution, we can obtain the pure enantiomers, and we see in the circular dichroism that these compounds have typical signature of LEHN. So we have been able to construct organometallic LEHN, and through the theoretical calculation, we can see that the metal is fully involved in the pi conjugated backbone. So when you play with the metal, you can combine the property of the helical molecule with the property of the metal. So this strategy is quite powerful because it enables to have a great diversity of LEHN. For example, a platina 6 LEHN, a bis platina 6 LEHN, a platina 8 LEHN, or even a bis platina 10 LEHN. So, and also you can play with the ancillary ligand going from a sulfoxide and chlorine fluoro ligand to a typical ACAC ligand. So doing this, you have a series of enantiopure helical molecules with nice optical rotation. Of course, they increase when you increase the length of the LEHN. And because of the presence of the platinum, you end up with the compound having a nice red emission. They are all red emitters at room temperature, red phosphors. And also they display circularly polarized emission, so with positive signal for the right-handed molecule and negative signal for the left-handed molecule. So you can play also with different chemistry in organometallic chemistry. So the famous one is the NHC chemistry. So we can combine the chemistry of helicene with the chemistry of N-heterocyclic carbene. So combining the optical activity and photophysical properties with either catalytic activity or material science applications. And to show you the structural diversity that we can create, I will show you that we can graft NHC onto a helix. We can prepare fused, helically fused NHCs. I don't know if it works, this one. And we can prepare also LEHN grafted on the nitrogen of the NHC. Okay, I will do like that if I can. So you can graft LEHN and imidazolium through CH2, and you end up with this iridium complex. But in this case, if you work with the small LEHN, you have chirality, but chirality coming from the iridium center. So the iridium has 4 different groups, and then you end up with stereochemistry S or R at the iridium. And if you graft a longer LEHN, a 6 LEHN, then you end up with a complex having both the LEHN chirality and the iridium chirality. So potentially you have 4 diastereoisomers. And okay. And then if you look at the NMR, you will see that you have only 1 pair of diastereoisomers, which means that there is an induction of chirality from the LEHN to the iridium. So the chirality at the iridium is controlled by the helical backbone. And so again, here it's interesting to look at the chiroptical properties response. And well, with the iridium.
Excuse-moi.
Regarde.
Je peux continuer comme ça, hein, t'inquiète.
Non, mais c'est qu'il n'y a plus le... Je ne sais pas comment la fermer. Ok.
Okay, sorry for the... As I was saying, we have the opportunity to compare the chiroptical properties of this iridium at chiral iridium complexes and the one with the LEHN. And as you can see, the chiroptical response are much stronger for the LEHN derivative compared to the chiral iridium complex. And through the theoretical calculation, we can see how the metal, the LEHN, and the NHC are involved in these electronic transitions. And there is an intimate interaction between the metal and the LEHN. So another type of iridium complexes that are very interesting are these cycloiridiatic complexes. So typically, this complex having two phenylpyridine compounds and a NHC pyrimidine derivative. So these are display typical blue emission, so blue phosphorescence, and they are very attractive for OLED technology. So Forrest and Thompson have made very nice research on this domain. So we were wondering if it was possible to prepare similar type of compound incorporating a helical backbone. But if we play with this type of compound, you have to play with stereochemistry. So you have the chirality of the helical ligand, and you have the stereochemistry at the iridium. So first of all, you can have either facial or meridional geometry. And on top of that, you have the delta lambda chirality. So you deal with many stereoisomers, but then you can control the chemistry. For example, so we have been able to develop this type of helically fused imidazolium, so for the first time in this imidazolium chemistry, and we play with the precursor that has a trans geometry, and doing that you end up with two type of complex with which has a meridional geometry, so controlled by the trans precursor, and then you can have either P or M helix and delta or lambda helix. And these compounds, because they are neutral and stable, you can separate all the stereoisomers by HPLC. And then when you have done this, you can study the chaotical properties, so especially the circular dichroism. And as you can see, both diastereoisomeric pair have same band, but with different signs depending on the enantiomeric pair. And more interestingly are the emission properties and circularly polarized luminescence, because this compound, they emit green phosphorescence if you compare to the model without LEHN, so it's redshifted, but they have nice CPL activity with a kind of mismatch effect depending on the diastereoisomer you work with. So if you have the P delta and P lambda, so by choosing the best one, you can increase the CPL response. And on top of that, if you look at the model, so it's a blue phosphorescent, but with a short lifetime. And with the LEHN, you go to a very long life phosphorescence. You see here, 250 microseconds. It's quite long. So the presence of the LEHN has a huge impact on the final photophysical properties and chaotical properties. So as I said, you can also graft LEHN on the nitrogen of the imidazolium salt, and you can do similar iridium chemistry. And doing this, you have a couple of two enantiomers, because the LEHN is too small to have a configurational stability. But still, you have a nice phosphorescent properties, circularly polarized phosphorescence with a good dissymmetry factor. And again, you have this long-lived phosphorescent with almost 1 millisecond in the solid state. And even more recently, we have been able to synthesize this twist-scale type molecules. So with one iridium decorated with 3 helical ligand. So it's stereochemistry is quite complicated because you have a mixture of this compound, but still this compound are chiral. You can separate them, and they display circularly polarized emission. But okay, if you have 3 ligand, it's beautiful molecule, but there is no particular advantage compared to having only one small LEHN. You can also play with the different metal. So if you go from iridium to rhenium, So rhenium has is a special stereochemistry. You can define either anti-clockwise or clockwise stereochemistry. And so you combine it with the chirality of the LEHN. And again, this compound, chiral, they are emissive, they emit green phosphorescent. And depending on the stereochemistry of the metal compared to the LEHN, you can end up with very different circularly polarized emission response. Sorry, difficult to talk with a mask. So also here, what was interesting in this case is the influence of the halogen on the rhenium. Depending of the halogen, so iodine or chlorine, you have very different emission properties, and also depending on the diastereoisomer. So we play with the stereochemistry of the metal, and we can have an impact on the quantum yield and lifetime. So it means that depending on the place of the halogen in comparison to the helical backbone, it can be either protected by the LEHN or more prone to be activated by the surrounding solvent. So there is an overall of the LEHN which protects from the surroundings and can help to improve the emission properties. So as Anne said, we have the chance to publish in the European Journal of Organic Chemistry, and we have reported these gold complexes bearing NHC ligand. And recently also in collaboration with a group at the LCC in Toulouse, they have been able to prepare helical molecules with a metal, the gold, which is well placed compared to the helical backbone to be effective in enantioselective catalysis. So these complexes are L-shaped, and they have central, axial, and helical chirality, and the combination of all these features helps to be efficient in enantioselective catalysis, which is quite difficult to attain with a helical ligand. So let's go now to another aspect of LEHN chemistry, which I call LEHN in action. So it's the use of LEHN in chiroptical switches. So a typical example is this dithionine ethane derivative with N that you can transform using light to a helical backbone, and you can use another light to cut the bond and to go back to the initial state. And doing this, you can switch between two forms. So you have a chiroptical switch displaying either strong optical rotation, if it's LEHN backbone, sorry, or smaller optical rotation when you have a pi9 derivative. So this is very interesting, the field of chiroptical switches, where you use the chiroptical activity to read out the system. So you can apply different external stimuli. You can apply redox potential. You can apply light. You can apply the chemical compound. So, and it's very interesting for many applications. So in this field, what are we doing? We are grafting some metal to a LEHN and play with the redox properties of the metal to change, to have an effect on the properties of the LEHN itself. And we play with some coordination chemistry. Through coordination, we can change the conformation of the system. So typically, we prepare this helical backbone with alkene, and we can graft iron. We can graft either 1 or 2 ions. So here are the X-ray structure. And doing this, already, if you look at the characteristical properties and the CD, you see some new bands appearing due to the presence of the metal. So you have MLCT type transition, which are quite strong. And you can see also in the molecular orbitals how the metal is involved in the orbitals of the whole molecules, and how it interacts with the orbitals of the LEHN. Then you can play with the redox activity of this type of compound. So if you have the neutral molecule here with the typical fingerprint of in the CD, you oxidize the molecule, and if you follow through electrochemistry, you can see that some bands are increasing and some other are decreasing, and some new bands are appearing in the near infrared region. And if you do it reversibly, then you can do several steps and you end up with a characteristical switch with the readout through CD response. And what was interesting here is with a physicist in Rennes, we were able to look at the characteristical response in the telecommunication domain, so at 1.5 microns. And here you see, if you measure the optical rotation for the left-handed LEHN, you have a negative response. You oxidize the compound, and the optical rotation goes to positive response. So you don't touch the molecule, the LEHN, you just apply a redox potential, and you have a strong change in the characteristical properties. So this enables to put an additional tag on the chiral molecule. And finally, I'm on time. So we have also developed some classical coordination chemistry, preparing this terpyridine ligand with 2 LEHN and playing with coordination chemistry. So the terpyridine will have this W-shaped geometry because of the 3 nitrogen that are in antiposition. You coordinate to zinc and you go to the U shape. And doing this, you induce some rotation of the ligand, so some molecular motion. It's not controlled, it's not unidirectional, but we start to see some conformational changes. And you can follow this nicely by spectroscopy. So you see the change in UV when you add aliquots of the zinc acetate. You see the CD, which nicely change. You see also the fluorescence. And this, you can explain this looking at the molecular orbitals, because in the ligand, you go through an extended pi conjugated system, so helical pi conjugated system, to a system where you have an intraligand charge transfer, so from the LEHN to the zinc metal. And again, nicely, you can see, you can follow also the circularly polarized luminescence, so from the ligand to the complex. And formally, you have a circularly polarized luminescent switch. And also, you can prepare this BP ligand with 2 LEHN, and this one behaves as a molecular hinge. So when you put some zinc acetate, you have the hinge which rotates, and they have this type of molecular motion. You follow it by CPL. We have now our own apparatus in Rennes. We can follow the CPL response. So when you apply zinc, you can also apply, so make some protonation, and you go to the red emission, and you see you have a system with free response that you can read out through different methods, CD, CPL, and so on. So I'm finished now. I hope I convince you that with LEHN chemistry, we can do a lot of different area of research. We can use them as characteristical switch in particularly polarized OLEDs. We can create structural diversity and make LEHN in action. And also, very importantly is a fundamental aspect which deals with how the characteristical properties change when you modify the system. So it's important also for theoreticians. They are very good model for theoreticians who are working in chirality. So before finishing, so I want to thank again all the group, and especially Ludovic Favreau and Muriel Lister and Pierre-Antoine Bouy, who are the other permanent researcher of the group. All the students who are involved in the result I have presented today, all my collaborators, and of course all the funding agency, without whom I couldn't also do my work. And thank you very much for your attention.
Thank you very much, Jeanne, for this talk. I heard it's not so easy to speak with a mask, and thank you for this effort. Thank you for this very nice presentation and all that we can do with their LEHNs and their characteristical properties. That's fascinating. We have time because Jeanne took a really time. We have time for questions in the audience. There is also possible to ask questions on the chat, and we have time at the end of the session. We will take some questions from the chat. So please, who wants to start? Yes.
Hello, thanks for your nice talk. I was wondering, did you try any other application for your material, like portraits or maybe OBLE? Because it seems to be the perfect structure to do that.
Yes, actually, one of the first examples I showed with naphtha limit, so donor acceptor compound, they have been incorporated into photovoltaic devices because they are good acceptors, so they can replace fullerene derivatives we usually have. And in this case, the chirality is interesting, but from another point of view, it's because in the solid state, when you play with racemic or enantiopure compounds, you have different properties in the solid state. So we have shown that when you use enantiopure compound, you improve the performance of the photovoltaic device because the charge transport is more efficient. So it's indeed very interesting in photovoltaic technology.
Thank you.
Thank you. Another question? Yes, Mathieu Solou.
Thank you very much, Jeanne. It's always fascinating to hear about chirality and all these kinds of crazy chirality. I have two basic questions. I mean, when you spoke about all your helicins that you make, you resolve them afterwards. Is it worth doing an enantioselective
yes, of course.
Those, or is it too complicated and now it's more simple to do the resolution?
Yes, so the resolution is so direct and straightforward. Usually, almost all our compounds we send to our collaborators in Marseille, they are able to separate them, except when they are charged. So, for example, the imidazolium derivatives, it's more complicated. So, in this case, it would be better to have some other method. The problem is that if you develop another method, it will be good for one specific compound, but usually it's not general. So, for example, in the case of the platina helicins, we were able to use a chiral sulfoxide on the metal and to make diastereoisomer. But then if you change the class of molecules, you have to develop something else. So there is no universal method except the HPLC one.
Just a second question about your OLED emitting, sorry, the OLED emitting circularly polarized light. What is the application of that?
So you use, when you go to the cinema to see 3D movies, so you use circularly polarized light in the glasses. One is left, the other one is right. So this is a direct application. And in OLEDs, actually, when you have a classical OLEDs, they put polarizer in it, like in the sunglasses. And actually, when they do this technology, they lose half of the light because of the reflection. When you reflect the light through this polarizer, you have half of the light which is blocked and doesn't go out of the device, so, which is a pity. So if you would use directly a molecule which would emit a circularly polarized light, you will recover all the light, the entireness of the light. So really there is a technological aspect which is really, really attractive.
Congratulations, Jeanne, for this very nice presentation. Just a short question related to your.
Can you please speak in the
Thank you. Just a short question related to the development of your helicene iron phosphine complexes. So did you try to make some catalytic applications of this complex? Would it be possible to envisage to
some catalytic application on this compound, not directly, because this compound are actually developed for their photophysical application, because they are stable, and so they are stable. So they are nice also for nonlinear optics, for example. So the book on the iron are on purpose for having a stable compound, because when you oxidize them, you have to keep them really without any decomposition. Otherwise, if they have some catalytic activity, then they will react. But the catalytic aspect is more tricky. As I said, it's interesting. We have one example, so but you have really to play with the position of the metallic center very close to the chiral environment. Otherwise, it's not efficient at all. So compared to the classical binaptide system, it's less developed and less appealing from the catalytic point of view.
We have time for some more questions from the, yes, sorry. Okay, please, Christophe, and then Jacques.
That's really a wonderful. So I wondered if you have, for example, those properties with solutions of different concentrations. Can you observe sometimes also supramolecular effects packing, especially, for example, for the platinum complexes? So
since it's a 3D molecule and quite globular, let's say, we don't see so much stacking. We see some pi-pi interaction and heterochiral or homochiral assembly in the solid state, but in solution, not that much. But recently, we have been trying to graft some gelator, so some substituent that on purpose can self-assemble, and we have been able to make some fibers. So with LEHN and substituent that can do hydrogen bonding, and we got very nice helical fiber that we can observe by microscopy. So we are trying to do this, but we need to make some further molecular engineering.
That sounds very exciting.
Yes.
Thank you.
Last question for Jacques. Here, Stephen.
Thank you, Jeanne. Very nice lecture. I just have another basic question to add to this lecture. In the final part of your lecture, you showed that you could provoke the rotation of the system, but that of course around the metal, but that of course takes place in a random place, so you don't have any chiral system at the end. What about using a chiral salt? You know, with a chiral anion associated.
Yes.
Would that have any effect on the centralization?
I'm not sure, because the chiral salt, depending if you have an intimate pair or not, this is important. I think when I was thinking about how to go further in this area, usually when you have efficient motors with really controlled motion, you need to have a constraint to block the system even more. So for example, in Bent Behringer's motors, they have this cyclohexane, which when you change the conformation, it goes from the other side. So here, I think we would need to do that. We would need to graft the two helix, for example, to make a link. And then when you will coordinate, probably to release the constraint, it would rotate. But synthetically, it's complicated. With a pair of iron, I'm not sure the constraint is strong enough to induce this.
Thank you very much. Thank you very much for the conference, for the very nice discussion. And now it's time, Mathieu, if you can come to me, please, it would be great. Jeanne, the Organic Chemistry Division Prize is awarded to Mathieu takes his vest. Sorry, I didn't told you before. Sorry about that. So the DCU prize is awarded to an experienced chemist who has performed nationally and internationally recognized research work. Jeanne, the excellence, the originality of your work perfectly matches the meaning, the value, and the recognition that we wish to give to this award. So I'm very honored to present you with this prize, to which, of course, I associate all of the former committee of the DCO. So congratulations, and Mathieu is going to give you a
Thank you very much, everybody.
Thank you so much. So it's a little bit complicated to change the presentation. So perhaps I have. D'accord. Okay. So, but we're in time, so perhaps I will not make so much stress. Okay, I just here perhaps for the next speakers, please take care. It's a little bit a constraint, but to stay here near the microphone so that the people from the video conference can hear you, but it was perfect, Jeanne. Don't worry about that. We had really the people who can hear, but I can understand it's quite complicated, and also with the mask. Okay, so we are going on with the next conference. We're on time. And I'm also very pleased to introduce Yannick GEIGER. So Yannick has made his doctoral studies in Strasbourg in the team of Stéphane Belmain-Lapin. And he selected two topics: the use of chiral metallopolymers as materials in nonlinear optics, as well as nonlinear effects in asymmetric catalysis. He brilliantly defended his PhD in December 2019. Thank you very much, guys, for helping me. So, he defended his PhD thesis in 2019. Then he joined the group of Professor Otto in Groningen at the Stratton Institute for Chemistry in January 2021 as an all-life postdoctoral researcher to work on chiral self-sorting and amplification in self-replicators. So Yannick, the floor is yours, and we are really pleased to listen about your PhD work. So what about the pointer?
It's working now.
It's working now, so that's great. We have to point at the slide. Jeanne, c'était ton père.
Okay. Yes, thank you very much, Emmanuel, for the kind introduction. Thank you for the invitation, and for all of you for being here. It's a great pleasure to be again in a physical conference. And I'm very honored glad and honored to get the Henri KAGAN PhD award from the Division de Chimie Organique. No, does it? The pointer. It doesn't work anymore. Try now. Still not. It's old school way. So now it's better, and can this even the hours don't work. Yeah. It works for him, but not for me.
Morgan, you have to stay there.
It works. Just press this button. Okay, just one. I won't go further. All right, I promise. So that's my top. So yeah, so I said I'm very honored to get this this PhD award. Not only because Henri KAGAN is a great French chemist, but he's also kind of the daddy of my project, as you see in a few minutes. I didn't have the pleasure to see him in a conference or so, but I was told he would like to start with a question or to resume it with a question. And it would be something crazy like, can we estimate the enantioselectivity of a chiral catalyst? Or it's a racemic mixture. First sight makes no sense, but he would say, yes, you can. I did it. It works if you start with a symmetric bifunctional substrate, which can be 2 times functionalized to get 2 chiral centers. In the end, you have a mixture of meso compounds and chiral compounds, and the ratio of meso to chiral compounds will tell you what is the enantioselectivity of the catalyst. Another such question would be, can the product EE be higher than the catalyst EE? Again, makes no sense. Intuitively, we would all say, if you have, for example, 40% EE catalyst, the product EE will be at highest also 40%. So you'd be usually here on that straight line. But he found that actually the product EE can be much lower than expected, but also much wrong one. It's lower, but also much higher than expected. Call this a nonlinear effect, either a negative one or a positive one. The blue is a positive nonlinear effect. I found examples for that and could also modelize it. And one of the most famous examples for nonlinear effects is Noyori's DAIB ligand, which catalyzes the addition of dialkyl zinc reagents to aldehydes to form chiral alcohols. And he found that in this system, he could obtain a 95% EE product from an only 15% EE catalyst. So he got something almost anti-pure from something almost racemic. This is quite amazing for a couple of reasons. First, chiral amplification in general, this kind of thing is believed to play a key role in the origins of homochirality. So why we are built only of L amino acids and D sugars. And this is intrinsically linked to the origins of life. And also the nonlinear effects in general have proven to be very valuable tools for mechanistic studies in organic chemistry. And we'll see in a minute why, because it has always a lot to do with aggregation. So here I'll show how nonlinear effects can arise. There are several models for that. KAGAN made a couple of models, Noyori too, and we'll see here the one from Noyori. So the DAIB ligand reacts first with an equivalent of zinc to form the complexes you see here on the side. Those complexes don't want to stay alone, they form dimers. Now, if the ligand is not enantiomer, you have 2 options. Either you form the homochiral dimers, so here at the bottom are R and SS, or you form the heterochiral dimer, that's the RS on the top. And those have not the same thermodynamic stability. If the heterochiral one is preferred, and that is the case with the AB, then what happens is that the minor enantiomer, here in my example, it's the S enantiomer, is completely trapped within those dimers. Trapped because the dimers are inactive. They don't catalyze. The only catalytically active thing is the surplus of major enantiomer. And this is why in the EE always stays high, regardless of the catalyst. If the homochiral dimers are preferred, then we would form the RR as well as the SS dimers. And through a concentration effect, the EE of the pool, which is catalytically active, will go down. And this would lead to a negative nonlinear effect. So one more question that came from KAGAN was, can a scalemic catalyst be more enantioselective than the enantiopure one? So in other words, the enantiopure catalyst is bad, and an RS mixture gives better results. And he found, yes, this also can be true, at least in theory. And this works in his ML3 model, which is different than the Joris model we just showed before. Here it's only trimers catalyzing and being present overall. And that means you have actually two different catalysts. So the homochiral, like RRR and SSS, have a different enantioselectivity than the heterochiral dimers, like RS and also enantiomer. So here at 100% EE, you have only, this
just one, okay?
Thank you. At 100% EE, you have only the RR catalyst, which is active. As soon as you lower a bit the EE, you start to have also the RRS. And if this one is more active and more enantioselective, then the EE can go higher. In this example here, the maximum is reached at 90% ligand EE. And this is what he called a hyperpositive nonlinear effect. So it's even more positive than just positive. And he tried to find also experimental examples for that, but he didn't succeed. And this is where our group comes into play. We were studying addition of dialkyl zinc reagents to aldehydes, a bit like what I showed before in the Jori example, but with a different ligand. This here is an ephedrine-derived ligand, and benzyl ephedrine here with a benzyl group. And at that time, we were interested in nonlinear effects. It was the goal to look at this, but we didn't expect to find this true hyperpositive nonlinear effect. Enantiopure ligand gives a really mediocre product E of only 16%. If you lower the ligand EE, it goes up to 53 at only 5% ligand EE. Works also, this is the example of dimethyl zinc. Works also with diethyl zinc. The effect is just less strong, but basically it's the same. And we're really thrilled to find this. This is something which is really cool, but gave rise also to a lot of questions. If you compare now the two, our system here cannot follow KAGAN's ML3 model. In the ML3 model, the curve can be hyperpositive only here in the upper half of the ligand EE scale, but we have our maximum here at 5%. So this does follow a different system, a different mechanism. And the question is how? How is that possible? How does it work? So key observation we made right from the start is that the solution of the reaction mixture is homogeneous only if the ligand is enantiopure, so at this point. As soon as the ligand is scalemic, we see a white precipitate that comes once you add the dialkyl zinc reagent to the ligand. And we isolated this, hydrolyzed it, and found back the ligand in its racemic form. So we have something a little bit like shown in the Jori model. We have here a racemate, which is kind of trapped and inactive here because it's precipitates. That means what remains in solution is only the major enantiomer, here the R enantiomer, in form of monomers and dimers. That we could verify by proton and dose NMR. So we see that dimers and monomers are present during the reaction. There are also trimers, only before and after. During the reaction, they do not exist. And now let's think a bit. Here, at 100% EE, all of the catalysts in solution have a quite high catalyst concentration. If we go down, for example, to 20% EE, then only 20% of the catalyst is in solution. The remaining 80% have precipitated in form of racemates. So it means we have the lower the EE, the lower the catalyst concentration. We can therefore expect that most of the dimerization happens here at high ligand EE. At low ligand EE, we'll rather have monomers. But now if actually both catalyze, not just the monomer like in the Noyori model, but also the dimer, both catalyze, but with different enantioselectivity. The monomer gives a high product E. This is why we have here high product E's, but the dimer gives a low product E, and this is why we are here at 16%. And further studies turned out to point exactly into this. So to verify this, we did a catalyst loading screening. So with only this time enantiopure ligand, but at different catalyst loadings. And we could reproduce what we see in the hyperpositive nonlinear effect. Here at high catalyst loading, we start with a low product E, but that goes gradually up the lower the catalyst concentration is. And that curve fits very well with the hyperpositive nonlinear effect. So this confirms the dependence on catalyst concentration. So did also further studies, so already mentioned the dose NMR. We looked also a bit at the product EE versus time, especially in the early part of the reaction. And we saw that this catalyst concentration effect is already at the very beginning of the reaction. So even here, the first point is at circa 1% conversion. Already there, we have a much higher product EE if we have a low catalyst loading. So this shows that this can be not just from the effects from the product being formed or so. Then we observed also an inverse temperature effect. The higher temperature, the higher also the product EE. Usually it's the other way around. And this goes very well with a model where we have dimers which are favored at low temperature, which break up as soon as you heat into monomers, which give higher product EE. And also important was to plot the kinetic ordering catalyst against the catalyst loading, which we got here this strange U-shaped curve. There are a couple of curves, for example, which are asymptotic or maybe linear or so, but a U-shaped curve has, as far as we know, never been observed. And we see later this is also compatible with the model we propose. Further insights were gotten also by changing a bit the ligand. So all what you've just seen was made with the NBE ligand here with the benzyl group. NME and metal-ephedrine, with just two metal groups here, behaves quite the same. So here in the catalyst loading screening, you see the product E also increases as soon as you lower the catalyst loading. But the overall EE is lower, and you see here 21%, it starts at negative values. So here we'll make mostly the S products. As soon as we lower the catalyst loading, get positive values, so we make mostly here the R products. What does it tell us? The dimer doesn't just give the same product in a lower EE, it actually makes the opposite product enantiomer. Dimer makes mostly the S products, while the monomer gives mostly the R products. This system is also enantiodivergent, and we obtained also even enantiodivergent nonlinear effects. Next part of the project was then to have a look at the theoretical side of the thing. So we have here general model, which includes dimers, homochiral, heterochiral, which are linked to monomers via dimerization constants. All of these entities are able to catalyze the reaction with a certain kinetic constant and certain antiselectivities to give the products with certain E. So this can be translated into mathematical equations, which allows to simulate nonlinear effect curves. And with that model, we are actually able to simulate hyperpositive NLEs quite similar to those we observe experimentally. And moreover, we could also simulate those catalyst order versus catalyst loading plots. And we obtained also one which is U-shaped. It's not exactly the same as seen before, especially here the scale is different. One should keep in mind that this model here is actually very simplistic. Doesn't include the influence of the substrate and the reagent on those different equilibria, also not that of the product. But it is sufficient to reproduce the main features we see, which are hyperpositive nonlinear effects, and a curve here which has a minimum and which is U-shaped. So, and lastly, I'd like to finish with a special or funny case. This was actually one of the first results I got in my PhD, and then after all what I've just shown you, looking back, raised a couple of questions. So this here is an LE curve obtained from the second ligand here at metal ephedrine, this time with diethyl zinc, not diethyl zinc. It is a bit different from the NBE system in the way that we have no racemic precipitate. And we see here there is nothing. It's linear. There's no nonlinear effect, nothing to see here. This is strange. This usually means, and this is why NLEs are used as mechanistic probes, if you have no nonlinear effects, it usually means there is no catalyst aggregation. If there is a nonlinear effect, then there is catalyst aggregation. And although there are already here some examples known, but this is quite striking because why should this, together with diethyl zinc, make no aggregates? This doesn't make sense after all we know now from the previous stuff. I made a couple of more studies and also now the well-known catalyst loading screening. And we see here, indeed, the lower the catalyst loading, the higher the product E, as before. The amplitude here is lower. As said, with diethyl zinc, the effect is not as strong, but it's measurable. Here we have a difference of around 10%. And here, as a comparison, there is also the same experiment with NBE, and we see it behaves quite the same. And we know NBE does form dimers, which are catalytically active. That's why we have these curves. So this seems, although we have a linear effect, you still have that thing with dimers and monomers being active. And NMR studies confirm that, yes, there are aggregates indeed. So why is there no nonlinear effect? This is, well, just a result of pure coincidence. Different components of the reaction, so all the different dimers, monomers, etc., they catalyze in a way that they compensate each other's actions so that the curve seems linear, but there's still aggregation. And using our model, we found that there's actually a multitude of different parameter combinations which can lead to linear plots, although there is aggregation. So here, this is, I think, a good lesson to retain. Linearity here doesn't necessarily mean it comes from the absence of aggregates. So with that, I'd like to conclude. We found the first experimental evidence for hyperpositive nonlinear effect. That is pretty cool, but I think the even most important thing is it learned something. It gave us some information about the system, and especially about a chemistry which is, come on, it's old. Diethyl zinc additions. This was done in the 90s. There's plenty of literature about that, especially with ephedrine ligands catalyzing. But whenever people were working on that, well, they referred to the Naioli model and didn't look further. And still in that 20 years old chemistry, there are nice things to discover, nice things to see. And I think they can have impact also on other systems. I think there are for sure other ephedrine ligands where there's also this thing with dimers and monomers being both active. And maybe there are even more systems where this has just been overlooked. It shows also, again, how valuable being interested, not just in molecules, but curves like this, can give you nice insights into mechanistic reactions and networks and so on. So with that, this is the end of my talk. I had 4 nice years in Strasbourg doing my PhD in the little bit of extra, and I'd like to thank all the people at the Institut de Physique et Chimie des Matériaux de Strasbourg, IPCM, at the DMO department, so all the students, fellow students I had, PhD students, master students, technical stuff, permanent researchers, and special thanks to these two people here, also present in the audience, Stéphane Bellemin and Thierry Achard, who are the best supervisors and colleagues I could have ever imagined. And with that, also thanks to all the institutes, the funding agencies, especially to the Ministère de l'Enseignement Supérieur de la Recherche, for which with all their scholarship, this project here would have never existed. Thank you very much.
Fascinating and very clear talk. Really, thank you very much, Yannick, for this presentation. We have time for some short questions. Yes, please.
Thanks for this very nice talk. I wanted to know if you try to modify a bit the ligand, for example, to make it bigger, to prevent aggregation, replacing, for example, the density by a tritone, to see if you can go back to.
We didn't play that much with the substituents. I did benzyl groups with a bromine or metal just to see if there's, but there wasn't not much change. What we know just is the benzyl group, at least having their aromatic moiety, is crucial to make the racemate precipitate. But would be a nice thing to do. Yeah.
Yes, please.
Yeah, really beautiful result. One of the highlights really in this field. Very well presented also. So I just wondered, did you also consider what would happen theoretically if this would be an autocatalytic system? And also,
okay,
in principle, when you have no divergence, could it be that you would have kind of an oscillating production of different
this is a wonderful idea. I would have to think about that, but having oscillating reactions with oscillating between plus and minus, spontaneous, just like this, I would say there must be a way, although I would have to look more into detail. Maybe we can discuss that later. So a very nice idea. Yeah.
Another question? I have a short question to you. You manage the active species by aggregation depending on the concentration. So you played on the concentration. Is it, of course, also possible to manage different aggregation with the changing the solvent? And my second point is, I understand the most enantioselective catalyst is the monomer form. What about then, sorry for this word, but what about the productivity of the system then at low catalyst concentration?
So, second question first.
Solvent.
You can, let's first talk of the solvent. In diethyl zinc chemistry, don't have a big choice of solvents. Diethyl zinc reacts everything which has a somehow acidic proton or so. You should influence the aggregation state by the solvent, especially if you have something coordinating. I think ether already has effect, and especially THF would surely prevent dimer formation, at least temper it. But it also has an effect on the catalytic reaction itself and also on the background reaction. Okay. So this is why THF is never used for that. For the other question, productivity. So when you lower the catalyst loading, you lower also the reaction rates, but not in a linear way. Okay. So this we haven't looked in detail. I suspect the monomer is technically more active than the dimer, so then the reaction speed doesn't lower as much as it should. This is something you're also able to modelize.
Thank you so much. A short question from the chat. If no, if there is this one. La.
Thanks. So the question is, I would like to know if you have any idea of why, when using NME, the product configuration has switched with the increase of NME. concentration.
So basically why there is this enantiomer divergence, why dimer gives negative EEs and monomer gives positive EEs. Why? For that, we would need to know more about the structure of the transition state and how the reagents bind to the two different catalysts. But just one thing I can mention here, there's actually a lot of precedent for that. There are a lot of catalytic systems where people made either just monomers or just dimers, and those had also this enantiodivergent effect. They didn't have both monomers and dimers in the same pots. This is new in that point. But this is actually something quite recurrent. Why it is recurrent, that is a very good question.
Thank you so much. So please join me to thank Yannick. I don't know, I'm not so sure. Well, I have a presentation, you know, where we can also see the middle, but it's quite complicated to change each time. Thank you very much, Morgan. That's great. It's okay. It's okay. So, okay, it's not a problem. Dear Yannick, I'm very pleased to present you with the KAGAN prize. And of course, it's really pretty well named for the topic of your PhD thesis. And we had not so much as the possibility to discuss with him about that, but he knows about your work, and it's very nice. This experimental proof of this hyperpositive nonlinear effect is really great. So all congratulations also from the former DCO committee. And thank you very much. So it's now time for the coffee break. The coffee break will be given here in the cluster. So you can go down to this place, and please take care about the time for the people who are online. We will begin again at 10:50.
Okay, so maybe we are going to start. So it's my great pleasure to introduce Julien Leclaire, who is awarded of Jean-Marie LEHN Award 2020. So Julien Leclaire studied at ENS Lyon, where he completed his master internship under the supervision of Professor André Collet and Lyndon Emsley. After a thesis between 2000 and 2003 at Paul Sabatier University in Toulouse, under the supervision of Dr. Jean-Pierre Majoral in the field of phosphorus bond reamers, he joined the team of Professor Jeremy Sanders at Cambridge University to develop dynamic combinatorial chemistry of sulfur edifies. In 2005, he was recruited as lecturer at École Centrale Marseille to join the chiroscience team of the Institute of Molecular Science of Marseille. His research work has focused on molecular and supramolecular interactions involved in enzymatic glycolysis. In 2013, okay, yes, sorry, he obtained the chair of chemistry from Labex IMEST, Institute of Multiscale Sciences and Technologies, and joined the University Claude Bernard Lyon 1 at the as a university professor. Currently responsible for the applied supramolecular chemistry team of the Institute of Molecular and Supramolecular Chemistry, Julien Leclaire used dynamic combinatorial chemistry for the recognition and extraction of molecules with high added value from complex mixture, extracted biological or industrial waste. So, Julien, it's your time now. Thank you.
Well, thank you very much. I first would like to apologize for not being here physically, but I'm afraid we've run an experiment in my home with my son, and it's a conclusive experiment, so I'm afraid I have to stay here. I'd like to thank, of course, the former committee of the DCO and the current committee of the DCO. It's a true honor to be here, even remotely today. And I'll switch my camera off so that the quality of the sound may be optimal, if you guys agree. So today I'd like to take you through a journey between molecular energy and information, and in particular to show you a couple of research projects we've been working on since I started my academic career here in Lyon. So when you start your academic career, of course, there are many questions coming to your mind. Well, you want to be successful, obviously, and to be successful, you have to push the boundary of knowledge. That's what we are supposed to do. But at the same time, you want also to have many grant proposals being accepted. And in that case, you have to show that your research will one day lead to some application that may be useful to the broadest audience. So the question is, which path should you follow when you start your career? Is it wiser to revisit concepts and try to find innovative ones and stick to fundamental chemistry? Or on the other way around, is it wiser nowadays to get some support in order to develop some disruptive innovation? And sometimes you have the feeling that you can't do both at the same time, and those two directions are opposed. I'll try to show to the youngest people that by seeking and by raising some fundamental questions, we ended up trying to develop some innovative technologies. So the topic we choose to investigate is, of course, a topic that has been studied by many giants in the field. And as it's been said in the introduction, it deals with molecular recognition, which consists in deciphering how molecules selectively and strongly bind to each other. Molecules can be host and guest, they can be building blocks. And that's what we started to do in the group when I arrived. By training, we all were organic chemists, so we started to study some very simple organic reaction. And this is the beginning of the, well, this is the reaction we started to study. They consist in CO2 capture by amine. As you can see, very simple organic reactions, nucleophilic addition on CO2 by an amine, which can lead to an ammonium carbamate, or the nucleophilic addition of water on CO2, which can lead to carbonate. This is, of course, a reaction that has many consequences in terms of carbon capture and global warming, and we've been trying to see if other simple reaction of organic chemistry could modulate, could displace those capture reactions that have an environmental and industrial importance. And later on, we tried to see if by combining non-covalent interactions that are in the right range in terms of energy, we could also choose, dictate what pathway can be followed during CO2 capture by simple organic molecules. And this consists in studying the interplay between non-covalent interaction and how they can affect and drive covalent chemistry, simple covalent chemistry. So the story starts with CO2 capture, which is obviously an important topic. CO2 capture in industrial units is conducted by using aqueous solution of amines. This happens in a big container, which is called the absorber, where the organic reaction takes place. It consists in the nucleophilic addition of one amine assisting by another amine as a base in order to lead an ammonium carbamate. This is a reaction that works very well. It's exothermic and it's entropically unfavored. What is the challenging step is the reverse step, which consists in stripping CO2 after its extraction from fumes in order to free purified CO2 for further application or storage and to regenerate the amine. That takes place in the dissolver unit over here in purple. And of course, to reverse the equilibrium, you need to apply what you have learned in thermodynamic classes, which are displacement equilibrium rules. Usually it is performed by injecting some steam, so by reversing the equilibrium using temperature, as it is an associative process on one side, a dissociative process on the other side. Temperature does the job, and then CO2 is being compressed. The thing is, most of the cost of this operation comes from the generation of the steam and the heating of the solution, and then from the compression of the gas. Those represent most of the operational cost of the process, which leads to the final cost that industrial have to pay if they want to sequester and capture their emissions. So molecularly speaking, what is being done is a temperature swing to reverse a favorable equilibrium between a dissociated and an associated state in order to reverse the population. What we've chose to study is obviously a very simple alternative, is to operate at the same temperature in both compartments, but try to displace the equilibrium using the partial pressure of CO2. In other words, to use a compartment where CO2 is abundant, the flue gas, and a compartment where CO2 is diluted, which is the atmosphere. And of course, if you do that, you trade your temperature swing for pressure swing, your Van 't Hoff equilibrium displacement rule for the Chatelier's equilibrium displacement rule using partial pressure of CO2. And if you do that, the cyclic capacity, which is the number of CO2 molecules that you capture per mole of absorbent, is quite low, and the regeneration energy is quite high. So the third leverage you have if you want to displace an equilibrium in organic chemistry is to use a chemical partner, a binder that will either interact with the reactant or the product. And that's we try to investigate, can a very simple organic reactant such as an aldehyde be a competitor towards CO2? In other words, we created a process based on two anti-parallel reversible covalent reaction. In the first reaction, the aldehyde binds to the amine, and if the amine was initially bound to CO2, you strip your CO2 off. So in the dissolver unit, you inject your aldehyde displaces your CO2, liberate the amine binds to the aldehyde in order to form an oxazolidine. When you then inject your stripped amine bound to the aldehyde into the compartment where CO2 is present, as in fumes, then you displace your equilibrium in the other direction, which means that CO2 will bind to the amine, strip your aldehyde. The amine, which is liberated, will bind to CO2 and form the ammonium carbonate. So that's a very simple alternative to pressure or temperature swing. Using physics, we decided to use organic chemistry instead. And if you use an aldehyde that is volatile, then it gets vaporized and you can recondense it and recover. And with this, you only have a catalytic amount of free amine in solution between the two compartments, and you oscillate between a CO2-rich compartment where the CO2 is being captured and an aldehyde-rich compartment where the CO2 is being stripped. And indeed, we could see that compared to the cyclic capacity you can hope for using simply pressure, this increases the cyclic capacity by a factor more than 2, and the energy of regeneration is considerably reduced. So with this first proof of concept, we decided to see if these two organic reactions could work cooperatively instead of in an antagonist fashion. In other words, can reaction of an amine with a carbonyl group with an aldehyde or ketone can actually displace the equilibrium toward more capture. When you look at CO2 capture, when you introduce increasing amount of CO2, the amine gets progressively loaded until it gets saturated. And the curves, which are called the binding isotherm, have this characteristical shape, which are symptomatic of a single amine binding to a single molecule of CO2. What happens in nature when nature wants to transport some gas, such as in hemoglobin, is that usually nature uses multivalent system. In other words, systems that have multiple binding sites. And when nature does that, the binding isotherm have a sigmoidal shape, because the capturing system oscillates between a state with low affinity for the gas to a state with high affinity of the gas. And this is due to the fact that there are several binding sites which interact with each other. So what we try to do is to use an amine that has indeed several binding sites, but can react with an aldehyde in order to polymerize or oligomerize so that it will have more binding sites, and those binding sites can interact with each other. So the idea was this time to use an aldehyde in order to exalt the capture of CO2 and transform a simple amine into an oligomeric amine. In order to do that, and if you do that, when you mix an aldehyde with an amine, you obtain a high diversity of different types of adducts. But the idea is to trade this diversity, which is a large, highly disordered system, into a highly organized system when you inject your CO2. In other words, the entropy is transformed into enthalpy, which consists in the linkages you will create between the different building blocks. How did we do that? Well, we looked for an aldehyde that would be able to bind the amine, form polymer or oligomeric species, and then self-aggregate. So we simply screened several polyamines, such as those displayed here on the frame. We screened several aldehydes and polyaldehydes that would be able to reticulate the amine. Ideally, those guys bind to each other and produce some imines, but the reaction is not complete. But when you introduce your CO2, then the equilibrium is displaced, the system polymerizes from low molecular state to high molecular state, and CO2 is being incorporated. And we indeed could find one pair of reactants that was actually producing some low molecular weight imines in the absence of CO2, and was yielding some high molecular weight oligomers in the presence of CO2 quantitatively. So we found a system that was cooperative in terms of binding, and we just investigate whether the properties in terms of CO2 capture, the energetic properties in terms of CO2 capture, were the one we hoped for with a cooperative system. And indeed, the temperature of desorption is much lower than what you have with a simple amine without the aldehyde. And the energy you need to inject to the system to dissociate it and to expel CO2 is also much lower than what you have with a simple amine. Of course, we wanted to know what was the secret in terms of structure behind this strange behavior. And then we had to bind a tool in order to investigate what was our network, our system, which was precipitating in the solid phase. And for that, we used NMR crystallography. To make a long story short, we compared the experimental spectra with the ones we predicted by modeling the crystals, and we ended up with this structure being identified. In this structure, every site is being used for hydrogen bond and salt bridge with nearest neighbor, which explains the cooperativity. But what is more striking is that the system is chiral. Also, you have made it with achiral building blocks. You've got asymmetric carbon here, which can have a S or R stereodescriptor, and you also have bicyclic system, which are atropoisomers, and the configuration of the atropoisomer is directly related to the chiral center. And we ended up elucidating by NMR crystallography the full configuration of the system, and ended up noticing that what we had obtained in terms of oligomers, which are tetramers of this phenyl ring, are purely homochiral. So starting from very achiral building block, we ended up with chirality being encoding, thanks to CO2 capture, into 8 bits of stereochemical information. Out of all the possibilities, only this one was chosen, and there was an interdependence between the stereocenter, the axial chirality, and the nearest neighbor. So we decided to follow this path and study how chirality and how stereochemical information could propagate during oligomerization process. Another topic which was investigated in the group was the formation of these cyclic oligomers which we call dinarine because they're analogs of pilarine, by disulfide bridge formation, which is reversible. Early on with Laurent, when we worked at the University of Cambridge, we had synthesized this building block, which in the presence of polyamine was exclusively yielding to this tetramer in physiological conditions. And when we isolated it and tested it, it ended up binding polyamine with very strong binding constants. And the modeling studies were revealing that we had, again, a homochiral species with disulfide bridges having a single dihedral angle of minus or plus 90 degrees, and all the carboxylate groups being oriented in the same way. So we're wondering why this is stereoselective and how can it happen to be stereoselective? Before addressing this question, we studied the behavior in terms of binding, and we ended up finding that our receptor was able to bind the polyamine even when it was interacting with DNA and changing its helicity, and our receptor was able to steal polyamine from left-handed DNA, encapsulate it, and restore the helicity of DNA to the right-handed helix. When we worked on this system again in the group, we reinvestigate the binding constant in water with Laurent, and we ended up finding that it was much higher than what we had previously measured by isothermal titration calorimetry. Indeed, it's in the picomolar range, which means that the energy of binding is something like 15 to 20% the energy of a covalent CC bond, and that's quite strong. And that means by supramolar chemistry, we can hope indeed to displace covalent equilibrium the way I showed you in the very first slide. But the idea was not to study energy first, but to study how stereochemical information can propagate when molecules self-assemble. How does the configuration of one bond, of one cycle, of one phase can be interrelated to the nearest neighbor? So we looked at the literature, and one of the seminal examples in dynamic combinatorial chemistry was the assembling of this metallohelicine by Jean-Marie LEHN in 1966. Remarkably, the polypyridine binding ligand was coordinating iron, and the shape and number of strands and metal nodes was templated by the anion, here the chloride. So what was published as remarkable was the selection of the number of different building blocks into a pentameric species, and indeed it was 2 pentameric species. When you look at the stereochemistry, what remained unnoticed until recently is that you only have one configuration in the metal node. It is either the P configuration everywhere on the metal complex, or the M configuration, or the delta, sorry, configuration on the metal complex, so the gamma or the delta. But what is striking is that also the helicity of the strand is interrelated to the configuration of the metal center. There is only one configuration that has been chosen by the system, and those configurations between helicity of the strand and the configuration of the metal center are interrelated. So we just wondered, okay, this is what happens with the helicates, but what happens with cyclophanes or with cavitans? Is it usual to have homochirality being propagated during self-assembly? And the answer is yes. When you consider 2 blockbusters, here are pilarines. During the chain growth, during the Friedel-Crafts reaction, you have an orientation of the methoxy group in the same direction until the ring closes, and you generally don't have this head-to-head positioning of the different substituents. So obviously, during the oligomerization, you have propagation of stereochemical information into the strand until ring closes. And that's also true for Kukovic reels, where you have concave and convex faces on the monomer. You only have the all concave configuration. The inverted one is quite rare, and this propagates once the strand grows until the ring closes. So obviously here, what dictates the positioning are steric interaction, and those are non-directional, non-covalent, but they can dictate the way molecules covalently assemble with each other. So what about our system? We had the chance to work with Jeanne in Munich and to get some crystal structure of our system. And what we can see is that indeed modeling was right. We were obtaining the homochiral species. All the disulfide bridges had the same plus or minus 90 configuration, all the same along the ring. And all the carboxylates were oriented in the same way in order to accommodate the steric hindrance. Indeed, the carboxylates have to be in the same axis than the disulfide bridge to minimize the steric hindrance, and here you only have room for the proton. So obviously, during polymerization using non-directional bonds, disulfide, and non-directional interactions, here the steric hindrance, you can encode stereochemical information. Because when you do the assembling, what we have in our tetramer with the help of an achiral amine and the use of an achiral building block is a homochiral species. All the blocks here with the carboxylate being oriented on the right side and the P configuration plus 90 degrees of the disulfide bridge. So this means by using two very simple achiral building blocks and non-covalent interaction, we can encode 8 bits of stereochemical information. There were indeed 16 possibilities in terms of distereoisomers, and we only obtained one of the 16 possibilities. So this is highly stereoselective. Okay, this was accidental. So we just wonder, can we actually encrypt stereochemical information and decide exactly what configuration we can make? First, we noticed that we obtained some crystals. Crystals were homochiral and the molecules were piling with each other, which means that if 8 letters were indeed binding to each other, we obtained nearest neighbor with the same configuration. Secondly, when we decided to encrypt stereochemical information, we synthesized these building blocks with 3 different types of CH bond with different types of hindrance. The blue ones are the more bulky, the green ones are slightly less bulky, and the gray ones are less bulky than the 2 other ones. We synthesize the cis isomer, the trans isomer, and these basically have this shape where all the bulkiness is on the blue side, and you've got also a little bit of bulkiness on the green side. And obviously they have different shapes and stereochemical information due to the hindrance. When we tested their ability to oligomerize doing disulfide chemistry, as expected, the cis one can oligomerize on the green side where there is the less bulky protons, whereas with this one, you have bulkiness on both faces of the monomer, and it cannot oligomerize, obviously, because the blue protons are too bulky. End of the day, they produce linear oligomers, but when it comes to cyclization, only the syn one is cyclizing. When the trans one is not cyclizing, it is degenerating by overoxidation and not doing disulfide chemistry any longer. So linear oligomers, which die into overoxidized species, this one is making cyclic oligomers. We had to analyze our system and to determine which size we had obtained with the cis building block, and we ended up obtaining 70% pure tetramer. This tetramer was analyzed by NMR, was analyzed by DFT calculation, and indeed our design was right. The bulky protons were outside, the less bulky protons were inside, and with the bulkiness of the gray protons, we could encode the right configuration on the disulfide bridging, which is the alternate PM-PM configuration. So in this case, by choosing the steric hindrance, we were able to encode 8 bits of information, selectively 1 diastereoisomer out of 24. If we increase the concentration, then we obtain some precipitate, and this precipitate was isolated 30%, and we had the chance to obtain the crystal structure. It was an octamer with exactly the right stereochemical information we had inputted, all the CH protons pointing inwards, and alternative configuration of the disulfide bridges, 1 single diastereoisomer out of 48, a highly stereoselective synthesis. So we resolve the crystal structure. I will skip that because it's becoming quite late. Coming back to energy, we ended up seeing that also we have the feeling in supramolecular chemistry that we need to have hosts and guests that have the same size. Indeed, we could show that information and energy are two different things. Because if butanediamine is the best host in terms of, is the best guest in terms of geometry with our host, what we could see is that the longer guest, which has an amine that protrudes from the cavity, is actually the best binder. And the reason for that is that when you took a longer guest than what you think by the lock and key principle, the guest and the host are both quite well solvated with water. They bind strongly with each other, but they have a layer of water on their polar ends, and this leads to the best binding enthalpy. So I'll probably skip those slides, which show that now we have merged our CO2 capture chemistry with supramolecular chemistry, and we can indeed use some hosts in order to bind the different types of molecules which capture CO2, and we can indeed reverse the CO2 binding equilibrium from carbamate to carbonate and increase the cyclic capacity of CO2 capture by displacing covalent equilibrium using non-covalent interaction.
Julien, please take care. The time is going, just 1 minute left. Thank you.
Thank you. So I'll keep that other example of supramolecular chemistry, just displacing CO2 capture equilibrium. I'll just end up by saying that now we've headed toward real application with our CO2 organic chemistry. We've used polyamine, which produce a collection of different CO2-based molecules. Those are binders for different types of ions, cations, and anions. And we have designed, indeed, we have deciphered exactly what molecules were produced by CO2 capture and how they can interact with different types of molecules. You can produce carbamates, they can hydrate, they can bind to each other, they can produce carbonates, they can bind to metals, and in that case, the metal strips CO2, then can bind to other metals and have CO2-rich groups. They can indeed make complex with other metals. And what we ended up deciphering is what type of ligand based on CO2 can selectively bind to which metal. So we ended up designing a process, and I will stop here, where we capture CO2 with amines. The industrial way it is done in facilities. So I'm skipping here. Amine binds to CO2, produces some CO2 decorated amine collections of molecules. They interact with metals that we are getting from all end of use batteries. These metals are being bound to the different collections of ligands we have produced by CO2 binding. They produce different complexes. Those complexes have different solubilities. And by decreasing the solubility polarity of the medium, we end up collecting the different metals individually. So we have designed a system where we bind CO2, produce a collection of ligands, then bind selectively to different metals and collect these metals. And this enables us to both capture and purify CO2 and both capture and purify metal at the same time. And this is nowadays, and I'll skip that, becoming a startup company that we have created, operating in water, processing 5 metals. This is the facility we have created called MakeRare with 7 employees. And we are launching our demonstrator, which is using CO2-based chemistry in order to process and purify some metals and recycle them and produce them for gigafactories, which are nowadays producing new lithium-ion batteries. So with this, and I'm sorry if I'm late, I'd like to thank all the supports we have, of course, the people who supported us to create some new knowledge about how molecules bind to each other, which information and energy, and of course, all the members of the group of the startup which have worked and contributed to these topics. And of course, thank you for your attention. Apologies for being long and remotely connected.
Thank you very much, Julien, for your great talk. Unfortunately, we are online and we have to follow the schedule. So I'm sorry to tell you that we have no time for the question, and I apologize really. But dear Julien, it's a real pleasure to give you that in real the Jean-Marie LEHN award. So just to remind the audience, this prize award, an advanced researcher or associate professor who is working in France and who is in between 8 and 15 years in his career. So congratulations of all the new board and the former one, board of the DCO. And congratulations also for your work. And of course, colleagues will give you this medal very soon.
Thank you very much.
So thank you very much. So we have now neural communication of Lucile ANTHORE-DALION, who is working as a researcher in the CER in Saclay. And she's going to talk about desoxygenation and no bonds. Thank you very much.
C'est bon, c'est déjà la troisième page. Ouais, mais c'est de partager.
Okay, well, thank you. And thank you for giving me the opportunity to present a part of my work today. So as said, I'm interested in the reactivity of an oxide, and I will show you why. So let's have a look at the natural nitrogen cycle. It's a well-balanced cycle where you're starting from dinitrogen. Nature is fixing nitrogen into ammonia, and at some point, this ammonia is oxidized into nitrogen oxides, which are deoxygenated back to dinitrogen. If we add on this cycle, the human activities, sorry, we cannot see it.
Try now.
Yeah, perfect. So now we can see it. The problem is that we are performing the first two steps via first the Haber-Bosch process, and then the oxidation either industrially or with all human activities. And the last step is ensured only by nature, which means since it has been estimated that we are fixing twice the amount of nitrogen nature can afford, we are accumulating nitrogen oxides into nature. So one way to maybe lower our impact on nature is to use those oxides as sources of nitrogen, so which will maybe able us to fix less nitrogen in there and make valuable compounds such as fertilizers or drugs, which we still need. This is not a completely new concept, and it's already known for quite a long time. You have some reaction like the nitration, which are used on industrial scale. The only problem is here, the nitric acid, which is used, is directly coming from ammonia, from the industrial oxidation of ammonia. So maybe we can improve this and also find new reactivities. So chemically speaking, for us as chemists, the question is, how do we break this bond? So you have a lot of questions about that. How do you interconvert the different oxides between them? How do you control the selectivity? And can we develop new synthetic applications? In the lab, we are interested in homogeneous catalysis. Why? Just because it helps us to develop new synthetic applications and also to understand the mechanisms behind this and to understand how we can break those bonds. When we jumped into this project 2 to 3 years ago, we were looking for a model molecule, a simple one. And we looked at the natural nitrogen cycle. You see you have a lot of different oxides in there. And we looked especially at the last step of the deoxygenation process, where you have this nitrous oxide deoxygenated to dinitrogen. This molecule, you might know it as a laughing gas. It's also becoming a public health problem right now, but we won't talk about that today. I'd like to emphasize the fact that this gas is a greenhouse gas, 300 times more potent than CO2. It's also the first ozone depleting substance, and the problem is it's highly kinetically stable. So it stays in the atmosphere, and it's difficult to remove from the air. Chemically speaking, for us as chemists, what we know is that nitrous oxide is a strong oxidant, but it's an inert molecule and a really poor ligand. So it's a rock, and we have to fight against this rock to activate it, although it's a strong oxidant. Nevertheless, there are some examples in the literature where homogeneous catalysis has been used to perform this reaction, the deoxygenation of nitrous oxide into dinitrogen. And Milstein reported in 2017 this ruthenium PNP complex, which is able to do it. And also very recently, Grismeyer and co-workers were able to show the same, to develop the same reaction with this bismetallic species. But when we started our project, we thought maybe we could make use of an analogy. The analogy is with a molecule we know quite well in the lab, carbon dioxide, because carbon dioxide and nitrous oxide are isoelectronic molecules. So, which means they could have the same reactivity. Moreover, if you look at the frontier orbitals, you have quite similar shapes. So maybe they could react the same. We wanted to know, to test this analogy with a really simple example. This is a reaction which has been developed by Skritskov in 2014, which who is able to deoxygenate carbon dioxide with disilines in presence of a simple fluoride catalyst. And what we did is that we just put 1 bar of nitrous oxide in presence of a disilane with a fluoride catalyst. And as you can see, more or less, this is the GC analysis. We have the disappearance of the nitrous oxide peak within 4 hours. And appearance, this is quite hard to see, I'm sorry, of the siloxane. This is working with different fluoride catalysts, but also with silanolate and alcoholate. You can see here, we still have a bit of nitrous oxide in all cases, or presence of hydrogen, residual hydrogen. But if we increase the Lewis acidity of disilane, we have a complete conversion within 2 hours or even 1 hour with just cesium fluoride. So this is a really nice system, but of course we wanted to know how it's working. The problem is, as you can see here, we have absolutely no intermediates. We cannot see them. So we went for DFT calculations, and what we believe is that the fluoride is reacting with the disilane to make this really reactive silane ion. The silane ion is able to add onto nitrous oxide with a quite low energetic barrier on the central nitrogen of nitrous oxide. As you can see here, the addition on the terminal nitrous nitrogen is quite high in energy. And then with this intermediate in hand, this intermediate, is ongoing barrierless pseudo-Brooke arrangement with release of dinitrogen. And this is a quite exothermic step. And it's making the silanolate, and the silanolate can either generate back this acetylene anion or the fluoride. And apparently we have two different cycles. Either fluoride is acting as a pre-catalyst or as a catalyst. And as you can see, the span of the two different reactions allows us to think that it's more pre-catalyst than a catalyst, but we cannot exclude that fluoride is also a catalyst in this reaction. So, well, with this, we thought, okay, this first analogy worked. Can we push it even further and use photocatalysis in this case? We got inspired by this work of Jean-Marie Laine in the 80s, who was showing that CO2 can be deoxygenated to carbon monoxide with this radium photocatalyst. Can we do this with nitrogen oxides? So the question is another, we are getting into another problem. If you look at CO chemistry, you see that you have a really narrow spectrum of redox potentials. What we want is a versatile catalyst, which is able to deoxygenate, if possible, all nitrogen oxides. So we have a much larger spectrum of redox potentials. Is it possible to do it? So let's start with a simple one, nitrous oxide. This is the work of Marianne's PhD. And what she did was to put nitrous oxide in presence of a photocatalyst. And as you can see, you have quite a nice production of dinitrogen. With all these different photocatalysts, so she was able to follow the kinetics thanks to this homemade system, which is airtight, because you have to notice that we are producing dinitrogen, and you have 80% of dinitrogen in air, so it's quite difficult to get a really airtight system. It's important to get an airtight system. And here, when we evaluated those 5 photocatalysts, in fact, the butyl substituted bispyridine here is the most potent. And she was able to get 86% yield in dinitrogen under ambient conditions still at 25 degrees, sorry, at room temperature. And then she was asking, okay, can I go to the very far at the opposite in the opposite direction of a scale? So we were here. Can we use this system to deoxygenate other nitrogen oxides? So here we went for pyridine and oxides with the same photocatalyst, so this diethyl substituted one. And she was able to show that pyridine and oxides can be deoxygenated under those conditions. In an even more fancy one, here you have a compound which you cannot obtain directly from the pyridine. You have to go first to the oxidized product and then to the reaction, which means you need a deoxygenation. And here she showed that this deoxygenation is performed at 82 with 82% yield. You might notice that the times here are quite different, and it's strongly depending on the electronic of pyridine and oxide. And here we have a strong correlation between the yield after 30 minutes and the sigma parameter, which means we have a really strong influence of this electronic. And it's probably due to the single electron transfer step. But we want to know more, and to know more about the mechanism of this reaction. Now it's a
completely different story. So we have to work with time results spectroscopy and also with spectroelectrochemistry with collaborators at CES, so Anna Maria Quaranta and Winfried Leibel, and in Grenoble, Cyril Constantin and Sylvie Charbon-Noblat, to understand what's going on in this reaction. So with that, I showed you our first results in the story of nitrogen oxides, and I hope to be able to show you more in the future, especially concerning the selectivity. I didn't talk about it today, and about the development of new reactivities. Finally, of course, I'd like to thank all people, especially Thibault, who is in the audience, for welcoming me in his lab, and also Marianne for her great job in her PhD, all collaborators, the funding agencies for their help, and you for your attention.
Thank you very much, Lucile. Great talk. We have time for a few questions.
Great talk, Lucile. Thank you very much. I'm intrigued as a simple organic chemist by your attack of your civil on the central nitrogen.
Yeah.
I see that. I saw that you make calculations, but how can you explain that to simple organic chemists?
This was also my question. In fact, when you look at the shape of the orbitals, it's you see that clearly the addition is on this nitrogen. It's really this. But I agree that this dipole, which is formed, is quite strange. But it's exactly the same reactivity for CO2. In fact,
it's probably.
I don't have a perfect answer as an organic chemist. I mean, it's also difficult for me to understand. And at the beginning, we just computed the first one, and we were quite wondering that the reaction was working at 20 degrees without any problem. And we had quite a high barrier, so this was puzzling us. So question?
Congratulations. I also have a question about the radium reactivity.
Yes.
So when you say oxygen to the pyridine, so
yeah.
The pyridine coordinates the radium and gives a charge complex, no? So this is typical reactivity.
This is an excellent question. So we are still working on that. And we still don't know if there is a real coordination of, there's no complex charge transfer for sure. So it's work ongoing. Apparently it's going through, so the mono-reduced species is not able to reduce the pyridine and oxide. So both in electrochemistry and photochemistry, it's not possible. So we have to go to a higher reduced species, and this is what we are looking at right now.
Okay, thank you very much. Maybe we can discuss. Now we are pleased to welcome Vincent Bizet, who is chargé de recherche au CNRS at the University of Strasbourg in the laboratoire d'innovation moléculaire et application. He is going to talk about germination of plants.
Okay, thank you for the kind introduction. First of all, I would like to thank the organizing committee for selecting my talk for today. So in our group, we are really interested about alkynes, and we can use this really small functional group for many transformations. So we can usually use it for the synthesis of nitrogen heterocycle using inverse electron demand disorder cyclization. We can also use it for hydrometallation. And we have also a special interest in fluorinated alkyne that we can use it, for example, recently for the synthesis of 2SF5 indoors. At this stage, if you allow me, I would like to make a small advertisement because we have 2 PhD positions available for next year on these 2 topics. So the first one about nitrogen heterocycle and the second one about organofluorine. So that's one. So now let's focus on the palladium catalyzed hydrometallation. So a few years ago, we developed hydrogenylation of trifluoromethylated alkynes. And in that case, the trifluoromethyl group is so electron withdrawing that in that case, it drives all the electrons toward the triple bond. And so the metalloid, so here the germanium or the tin, will always be oriented toward the alpha position. So we saw that if we change the alkyne by something a little bit less electron withdrawing, so in that case, something more rich, like enamides, would it be possible in that case to control the regioselectivity of the hydrometallation by playing on the ligand? Okay, the idea was to see if it would be the size of the electronics of the ligand would play this game. So of course, hydrometallation is known in the literature. And here I presented the example I found. So for example, hydrosilylation is well known with different transition metal. And what you can see is that in each case, the silicon is oriented into beta position toward the nitrogen. During this study, we also saw one example of germyl zincation of enamide, but that case as well, it was only introduced in beta position. For the hydrostanylation, one example of palladium catalyzed hydrostanylation is described, but once again, the tin is only introduced in alpha position. Okay, so now the aim of this study was to develop a radiodivergent system. So we selected this benchmark enamide, and as you can see, if we do the reaction, hopefully we can obviously we can make 4 different isomers, so the cis hydrogenylation and the trans hydrogenylation. And of course, starting from palladium tetrakis triphenylphosphine, we only get the cis addition. And we obtain mainly the compound 3A at 80%. And then optimizing a bit the ligand of this synthesis, what we found is that using DP-EFOS, we were able to increase the ratio up to 91 for the alpha product. During the same optimization, what we found is that if we use now cyclohexyl DP-EFOS, so not with the phenylphosphine, but cyclohexyl phosphine, in that case, we invert the selectivity and we made mainly the beta product. Okay, so we optimize again this condition, and what we found is that using a monophosphine, rich and bulky, so bisterbutyl methylphosphine, in that case, we were able to improve it up to 93% for the compound 4A. In 2015, so Professor Fürstner developed a really elegant method using ruthenium catalysis for doing radiodivergent hydrogenylation, and in that case, it was trans. So we said, okay, this would be perfect to complement our study, and if it's working, maybe we could get the 4 products. So we tested the condition, and obviously we did not get this one, but we got only compound 3A and 4A. And what is interesting is that even in that case, with the ruthenium catalyst, we still get this radiodivergence. Just to complete the study, we just did a radical hydrogenylation just to confirm that we were able to make the trans, but of course, in that case, the radio selectivity was not possible. So we did the scope of this reaction, first of all, by modifying the nitrogen part of the enamides. And as we can see, it's working with different type of enamides, carbamate and amide. And what we can notice is that if we decrease the size of the nitrogen part, the condition A, so for the alpha selectivity, will be improved. And at the opposite, if we use something bigger, in that case, the alpha is detrimental for the alpha selectivity, but it's better for the beta. And it's even more clear with the sulfonamide. Here we can see that with cyclic sulfonamide, we still have this dichotomy alpha-beta according to condition A and B. And since we open this chain and it's much bigger, then the alpha selectivity is almost lost. And by increasing the size, whatever the condition, we got only the beta. The variation of the R part was also studied. And in that case, you see it's working well most of the case. What we notice is that by adding an electron donating group on the aromatic, the alpha selectivity is usually improved. But then by adding an electron withdrawing group, in that case, the alpha is decreased, but then the beta is increased. The reaction is also compatible with alkyl chain. In that case, it's really chemoselective of the triple bond and not of the double bond. And these two last cases, if you put something really big in beta position, of course, the beta position is totally hindered, and then the germanium goes only in alpha, whatever the condition. And for this one, if it's a terminal enamide, the catalysis is still able to get up to 45% in the alpha condition, while in the beta, of course, the position is available, so 100%. We also extended this reaction to other germanium commercial source, so for example, ethyl and tributyl. In that case, the selectivity decreased a bit. But what is really interesting here is that we apply exactly the same condition to hydrostanylation, and in that case, we get 95 to 5 in both conditions. So this is the mechanism we propose. Normally, starting from palladium 0, the palladium should insert in this bond and make oxidative addition, then coordination to the enamide. And after, we normally a clockwise or anti-clockwise rotation should orient the ligand in one way or the other to form these two intermediate, 4A and 4B, which after reductive elimination should afford the two isomers we observed, 3 and 4. And what we did, we use a special substrate. So this one, an enamide with an allyl group. And in that case, what we confirm is that we really have this hydropalladation pathway. In fact, at this stage, we have these two intermediates. And since here the palladium is really close to the allyl group, the point is that the palladium can do a migratory insertion and after reductive elimination form this cycle. So this is the only product we observe, byproduct we observe during this reaction, proving the hydropalladation pathway. Of course, we wanted to confirm this experimental proof by using DFT calculation. So we started a collaboration with Professor Hauk, and we compare hydropalladation and germyl palladation. Of course, the hydropalladation was favored. And here as well, looking at the dihedral angled hydropalladation was favored. So it was here with a really simple system. And then we shifted to a more complex system, so really close to the condition A we developed before. So triphenylphosphine and triphenylgermane. And in that case, we got the two mechanisms, so hydropalladation and germyl palladation. And once again, the hydropalladation is favored. And if we look closer, we have the two intermediates for the alpha and the beta product. And in that case, the alpha product should be favored about 1 kcal. Shifting now to this bulkier ligand, so the bisterbutyl methyl phosphine. We calculated for the hydropalladation, and what we got is that in that case, the beta transition product here should be favored about 1.8 kcal. So it is totally in agreement with what we obtained experimentally, but we still don't have the answer about what is the key of this reaction. It means, is it the fact that the ligand is bulky, or is it the fact that the ligand is electron rich? So to confirm this, what we did is that we compute the same with trimethylphosphine, which is much smaller than this compound. And in that case, the calculation gave us the answer that normally, since it's smaller, we should favor the alpha hydrogermylation. So it was in theory. So we did the experiment to check. And in that case, what we obtained is this. We got, of course, the alpha product mainly, but you see the ratio is really low, 60 to 40. And here we are in a kind of mismatch situation where the fact that the small ligand will do the job for the alpha germylation. The problem is that trimethylphosphine is an electron-rich ligand. So is also playing the other way around. So the key here is to finally find a small ligand, but not too much rich, to favor the alpha. So this is the end of my talk. I hope I convince you that we develop a radiodivergent hydrometallation of enamides. We made some mechanistic investigation, and we point out the hydropyridation mechanism and the fact that the radioselectivity was controlled by the ligand. To finish, I would like to thank my collaborators. So first, Nicolas Blanchard, my collaborators and group leader. Vincent de Brever, who did most of this job. Ken Ark and Annette Turlik for calculation, the CNRS, and the INR GCJC for this project. Thank you very much.
Thank you very much, Vincent, for your nice talk. We have time for questions.
J'ai une question par rapport au type de substrat que vous utilisez. Do you think that the carbonyl moiety in your substrate can eventually coordinate with palladium in some of your intermediates?
Yeah, this is something possible. One of the main differences we observe between the carbonate and the sulfonamide, for example, this is really the two compounds with really the big difference in reactivity. And in that case, you know, with carbonate, the nitrogen is delocalized toward the CO. But with sulfonamide, in fact, the nitrogen cannot delocalize toward the SO2. So in that case, delocalize toward the alkyne. So this makes the biggest difference between the two. But we cannot exclude that the palladium is also coordinating to the CO, but I don't think it's coordinated to the SO2. I don't know if I answer to your question.
The question?
Thank you for the talk. You may have said it, but are you considering using other metals than palladium, or is it really interest in doing this, or performing the same type of reaction?
Yes, so for germanium and tin, palladium was really efficient. But if, for example, you want to do hydrosilylation, palladium is not the best metal, and it's better to change. For example, platinum would be better. I think we can probably extend this method to other metals.
Thank you.
Some question on the chat? We are going to say it again. But... And now it's my great pleasure to introduce Julie OBLE, who has been awarded of the Jean-Normand Prize in 2020. So briefly, Julie obtained her PhD in organic chemistry at ENSTA, École Polytechnique, in 2007 in Paris under the supervisions of Dr. Laurence Grimaud and Laurent Elkaïm. During this time, she studied the development of multi-component reactions with isocyanide and a new Hughes-Miles coupling. Between 2007 and 2008, she worked as a postdoc at the University de Montréal under the supervision of Professor André Charette, where she synthesized new amylabile ligands and applied them in asymmetric analysis. She then came back to France at Sorbonne University, where she obtained a postdoctoral position, then an lateral position, and between 2008 and 2010, under the supervision of Dr. Emmanuel Lacotte and Professor Serge Thorimbert and Bernard Hasenkopf, she studied the synthesis of functionalized polyoxometalates. Since September 2010, she is associate professor at Sorbonne University, and in June 2020, she obtained her habilitation à diriger les recherches. Her research interests are toward the implementation of new domino reaction, design new support for organometallic catalysts, and development of new CH activation reaction.
Thanks for this kind introduction. Hello, everybody.
First of all, I would like to thank the Division of Organic Chemistry, the former board for the award and the new board for the organization of this day, and for giving me the opportunity to present a part of my research carried out at the Institut Parisien de Chimie Moléculaire at Sorbonne University in the RUX team. So today we focus my presentation on a recent project that concern ruthenium catalyzed direct functionalization of biomass derived to formulate aromatic compounds. In the RUX teams, my researches are focused on organometallic catalysis with, on the one hand, the development of new domino reaction for the construction of polycyclic structures. On the other hand, I am also interested in the design of new support for organometallic catalyst. And recently, I am also interested in the development of new CH activation reaction on allylic and aromatic systems, as well as their use for the functionalization of biomass derivatives, such as furfural derivatives. So today, I will focus my talk only on the projects that concern the catalytic CH functionalization of furfural derivatives, and more generally of two formyl heteroaromatic compounds derived from biomass. So why biomass? Our planet's fossil raw material are irreversibly diminishing. Consequently, chemical industry, among others, must shift to renewable feedstocks. Biomass, in particular agricultural waste, are an alternative since they contain significant amount of hemicellulose. The acid hydrolysis and the cyclodehydration of these carbohydrates provide two components in particular, furfural and 5-hydroxymethyl furfural, which have been identified as two high-value products derived from biomass. So the transformation and the functionalization of these two products is currently a competitive area of research. The number of ways to convert directly or indirectly furfural into fuel or into useful industrial chemical compounds is colossal, including, for example, furfuryl alcohol and its tetrahydroderivative by reduction, or also, for example, furfuryl amine by reductive amminations. Furfural is also a key intermediate for the production of furan by catalytic decarbonation, and tetrahydrofuran by hydrogenation, thus offering an eco-compatible alternative to the petrochemical productions. Another importance of furfural comes from the ring cleavage, leading to other useful industrial compounds, for example, maleic anhydride or libulinic acids. So the development of new and modern strategy to decorate furfural is now desirable in order to obtain other useful industrial compounds. Furfural is composed by a formyl function, an aromatic nucleus, and 3 different CH bonds. So, in order to functionalize furfural by CH activation, the challenge is to selectively functionalize one of these 3 CH bonds. In particular, the C3 functionalization is uncommon and requires generally the use of more oxidate substrates, such as carboxylic acid, amine, or ester. So, at the beginning of this project, we wanted to develop a new method for the C3 functionalization of furfural via CH activation without prior modification of the redox state of the aldehyde functions. To start this project, we wanted to work on one reaction in particular, the Murray reaction, which is an hydrorelation of alkene, such as vinylsilane, under ruthenium catalyst. These reactions has been intensively described with ketone as the reacting group, as we can see in this example with the 2-acetyl furan. However, the use of aldehyde as the reacting group was inefficient, as we can verify at the beginning by performing different tests on furfural directly, leading to degradation or starting material. However, the use of aldimine, like in this example, this benzenic example, we can realize the Murray reaction in this ortho position. And we thought that this strategy using imine could circumvent the above problem and could allow the Murray reaction on furfural derivatives. So our first objective was to find the right type of conditions and the right type of imine that could render possible the Murray reaction on furfurylimine with various alkynes. So typical conditions and catalysts for the Murray reaction on aldimine were tested, such as vinyl selene as alkene partners, the tri-ruthenium dodecacarbonyl as the pre-catalyst, intolerant at high temperature. This is the work of Christopher Bezzetta, an Italian student during his laurea. Several furfurylimines were synthesized and testing, showing, for example, that this terbutyl furfurylimine was inefficient, whereas this N-benzyl, N-parametoxybenzyl, or N-parametoxyphenyl give very low yield. So, in order to increase the yield and to increase the stability of some intermediate along the catalytic cycle, we envisage to use a bidentate directing group like this kind of amino-imine directing group. And we're delighted to obtain the desired product from this kind of amino-imine using 3 equivalents of vinyl silane at 150 degrees. We can obtain the final product. It should be noticed that with this kind of aliphatic imine, the hydrolysis of the imines occurs during the purification on silica gel, leading directly to the C3 alkylated furfural derivatives. The use of this bidentate aminoimine directing group was efficient in order to realize the Murray reaction with various vinyl silane, trialkoxy, trialkyl, or triaryl vinyl selene. In a bracket here, where indicate the NMR yield of the reaction before purification, so the NMR of the C3 alkylated furfurylimine. We can also realize the reaction with styrene derivative. And in this case, we obtain a modest yield consisting of this mixture with the linear project and a small amount of the branched products. We can also use a C5 substituted furfural derivative like this TBS protected HMF derivative, or with a methyl in this position. However, phenyl in this C5 position slow considerably the reactions. After we wanted to investigate the catalytic cycle of this Murray reaction, and for that we realized some DFT calculation in collaboration with Professor Virus at the University of Lisbon. This calculation allowed us to confirm the importance of this bidentate directing group, which stabilized some intermediate along the catalytic cycle. First of all, we anticipate the formation of a mononuclear ruthenium carbonyl complex from the pre-catalyst, and this mononuclear ruthenium complex coordinates the 2 nitrogen of the bidentate directing group. Then, after a CH3H coordination, the oxidative addition step gives this ruthenium hydride intermediate. At this stage, we anticipate the mono decoordination of the amine, leading the coordination of the alkene, and then the insertion of this alkene into the vinyl silane into this ruthenium hydride bond, giving this ruthenium alkyl intermediate. Finally, a reductive amylation followed by a substrate to product ligand exchange give this final product, the C3 alkylated imines, and release this catalyst. After this first project, we were delighted to obtain the first example of C3 alkylations of furfurylimine. And this result led us to consider an extension toward the carbon-negative barrier using carbon monoxide as natural and cheaper C1 sources. To the best of our knowledge, there is only one example of a propionylation of furfurylimine from this kind of terbutyl furfurylimine using a pressure of carbon monoxide and pressure of ethylene. However, for her project, we wanted to use atmospheric pressure of carbon monoxide. And for that, we wanted to use to saturate the medium during 5-minute bubbling of CO. And then we can realize the reaction. Donc, after some optimization of the condition realized by 2 PhD, Fares Rosdesi and Roberto Sala, we can realize this carbonative mural reaction from this aromatic imine, this para-methoxyphenyl imines with various vinylsilane with the same catalyst as the triruthenium dodecacarbonyl in toluene. And we can obtain this C3 acylated imine from furfural, 5-methylfurfural, or the TBS or protecting HMF derivatives. In the case of this imine, this aromatic imine, which was more robust, we can isolate by purification on silica gel the C3 acylated imine, and then a simple acid hydrolysis give directly the C3 acylated furfural derivatives. It should be noticed that this aromatic imine, this para-methoxyphenyl imines, was inefficient in the classical mural reaction without CO atmosphere. Furthermore, the bidentate, which was efficient in the classical mural reaction, was inefficient under this condition with CO atmospheres. At this stage of this UV, we wanted to use other 2,4-methyl heterocycle, and we first consider the use of pyrrole 2-carboxaldehyde, since this compound can be considered as biomass derivative, since it can be obtained from furfural in one step via a partner synthesis, or in a sequence of 3-step reduction, Hashimotovic rearrangement, and Maillard condensations. First of all, we investigate the classical mural reaction without CO atmospheres, and from the various imines obtained from this N-benzyl pyrrole. This imine can react with vinylsilane with the same catalyst. And in this case of this bidentate imine, this para-methoxyphenyl imine, we obtain very low yield of these two products, the C3 alkylated product and the C3 acylated product, in which the CO comes from the pre-catalyst triruthenium dodecacarbonyl. However, after some experimentation in order to obtain only this product, the C3 alkylated product with good yield, we never arrived about that. So we next consider the optimization, only the optimization of the carbonative mural reaction. And for this heterocycle, this carbonative mural reactions was efficient from the aminoimine directing group, the bidentate directing group, and we can realize with the condition previously developed by saturating the middle during 5 minutes of bubbling, we can realize a carbonative mural reaction with various vinylsilane and also styrene derivative. And after purification on silica gel, we obtain directly the C3 acylated pyrrole 2-carboxaldehyde. In the case of styrene, as previously, we obtain a mixture between linear and branched products. Furthermore, with this heterocycle, we can also use the PMP imine, which was more robust and allows the use of more example of vinylsilane and more example of styrene derivative. So in this case, after the reaction in the condition previously developed, we can isolate the C3 acylated imine, and then acid hydrolysis give directly the C3 acylated pyrrole 2-carboxaldehyde. As previously, the catalytic cycle of this carbonative mural reaction was also investigated by DFT calculation for the furfural and also for the N-benzyl pyrrole. And in this slide, we can see the catalytic cycle for the N-benzyl pyrrole. As previously, for the classical mural reaction, we anticipate the formation of a mononuclear ruthenium carbonyl complex coordinated with the imine directed group and bearing two strip CO ligands. Then, after the oxidative addition and the insertion of the alkene into the ruthenium hydride bond, we obtain the ruthenium alkyl intermediate here, exactly as in the classical mural reactions. So now, under CO atmosphere, we propose a CO insertion into the ruthenium alkene bond leading to this ruthenium acyl intermediate coordinate with another CO ligand after the addition of another CO ligand. Then reductive eliminations followed by a substrate to produce ligand exchange give this final C3 acylated imine and regenerate this catalyst. During this to study on Murray carbonative Murray reaction, we also tested a lot of unsaturated partners. For example, indurant alkene or inolator or alkyne, disubstituted alkyne. And we never obtained the desired product in classical Murray or in carbonative Murray reaction. Also, in the case of electron-poor styrene derivative under CO atmosphere, we never obtained the acylated product. However, with acrylate derivative, we obtained an expected product. And this product, after some optimization, some analysis, was analyzed as the C3 alkylated product derived from Fujiwara-Moritani type reactions. And so this reaction was efficient always from the same imine, the paramethoxyphenyl imine, with 4 equivalent of acrylate, with the same catalyst, the triruthenium dodecacarbonyl. We can obtain this C3 alkylated product. We obtain the same yield under air or under R atmosphere, which means that the oxygen doesn't act as a sacrificial oxidant. And we speculate that the excess of acrylate can act as an hydrodissector, as we see after in the catalytic cycle. These new conditions of Fujiwara-Moritani type reaction catalyzed by ruthenium 0 seems to be efficient only on this kind of heterocycle. And the classical condition of Fujiwara-Moritani reaction with palladium 2 and ruthenium 2 were inefficient with this kind of heterocycle. Furthermore, we tested, of course, this condition on benzenic counterpart like this imine and this ketone. And with this condition catalyzed with ruthenium 0, give some traces of the orthofunctionalized products. So with this new condition, in order to realize the C3 alkylation, we investigate the scope. And so this reaction works well with furan-based PMP imine from furfural, 5-methylfurfural, CBS protecting HMF derivative with various acrylate derivative. We can also use pyrrole or indole-based 2-PMP imine, which with some acrylate derivative, and also some styrene, electron-poor styrene or vinyl sulfone. Donc the yield were better because this heterocycle were more stable than furan heterocycle. As usual, the mechanism was also investigated by DFT calculation in order to understand the difference between the Murray reaction with the vinyl silane and the Fujiwara-Moritani type reaction with electron-poor alkene like acrylate derivative. Donc after the first step, which are the same, donc the oxidative addition, we obtain this ruthenium hydride, the decomplexation of the directing group, and then the coordination of the alkene, we obtain this intermediate. So now, with this kind of electron-poor alkane, with the insertion of this alkene take place into this carbon ruthenium bond, this CsP2 ruthenium bond, leading to this intermediate, which undergo a dehydrorutination to obtain the final product. And this ruthenium dihydride intermediate coordinates again with another molecule of acrylate derivatives. Then another hydrorutination gives this intermediate, coordinate again with another molecule of imine. And finally, a reductive elimination gives this methylpropionate and regenerate this catalyst. In parallel of this study on Murray, carbonative Murray reaction, and also Fujiwara-Moritani type reaction, we also developed a method for the C3 reaction of furfurylimine catalyzed by ruthenium 0. This is the works of Valerian Ramis-Cladera and Philippa Siopa. And this reaction works from aromatic imine, electron-rich aromatic imine, donc obtained from this para and dimethyl aniline. And this imine can react with various boronic ester, neopentyl boronic ester, aryl or alkylidine, in presence of basylidene acetone as sacrificial hydride acceptor, with always the same catalyst, the triruthenium dodecacarbonyl. And we can obtain this C3 arylated or alkylated furfurylimine. Then HCl hydrolysis give the aldehyde C3 arylated or functional this method of ruthenium 0 catalyzed C3 arylation of furan derivative was also used in the collaborative project between our team and the team of Professor Alfonso and Philippa Siopa at the University of Lisbon with the PhD student João Ravesco. In this project, we developed a chemoselective sequence involving first an enzymatic monoamidation by flow chemistry of FDCA, the diester of FDCA, donc 2,5-decarboxylate furan. And with this enzyme, by flow chemistry, we can obtain this disubstituted furan with good productivity and good GC yield. And then, in batch, we can realize with more or less the same condition as previously developed from furfural derivative, we can obtain the C3 arylation in this position directed by the amine function, and we can obtain this furan trisubstituted with good yields. So I hope I have convinced for the importance to decorate furfural and in particular with ruthenium catalyst via the imine formation, which play an important role in the result. Finally, I would like to thank all the ROX teams, all the permanent, in particular Giovanni Poli. I would like to thank the students who work on this project on ruthenium catalyst. This Christopher Pezzetta, Fares Rodessi, Roberto Sala, Valerian Ramis-Cladera, and João Ravesco. I would like also to thank the current students who continue this project on the functionalization of furfural. Sebastian Kurpanen, who is developing a C3 silylated platform and who is defending his PhD on Friday. Grady Kala, who is developing some C3 functionalization or C5 functionalization by flow chemistry. And Alessia Mori, who is developing C4 functionalization of furfural. I would like also to thank our collaborators, Professor Veros for all the calculations, Professor Alfonso and Dr. Siopa for the collaboration and for the funding H2020, and in particular this recent project Biomass for Sampton. I would like to thank the cost and slash activation, the doctoral school, the LabEx Maiken, Sorbonne University, the CNRS, and you for your attention. Thank you very much, Julie, for your nice lecture. So we have time for a few questions.
Thank you for this very nice presentation. I have just one question concerning your methodology.
Yeah.
Actually, you are using two steps in methodology, starting from aldehyde, formation of imine, and after functionalization of the release of. I'm wondering just if you try to use the position there in your strategy. Starting to the aldehyde and using just a specific amount of.
Yeah, of course we try that. Of course, from the beginning we try that. The more or less best result that we obtain it is using 50% of amine, and it's not really good. And the problem in our condition, there is some degradation of the furan because there is some decarbonylation of the furfural. So it's more or less impossible in batch chemistry to realize this thing and using catalytic amount of amine. For the moment, we arrived by flow chemistry to realize what is not catalytic. We can realize first the imine functions, then the C3 acylation, for example, and then the hydrolysis. Everything by flow chemistry, it's work well. but it's not catalytic, so this is a problem.
So there is a question from Audrey Offran. I guess that was regarding the first part of your talk about the rural interaction.
Right.
Were you able to identify the intermediate shown by DFT, either the ruthenium zero active catalyst or the ruthenium 2 hydride complex by stoichiometric experiments, and show their involvement in the transformation?
Okay, if I understand well, if I arrive to analyze this, you can repeat?
No.
We never identify this in the stoichiometric condition. We don't realize a lot of stoichiometric conditions because it is very passive. The problem of this output catalyst, it is a trimer. For the moment, we don't know. For the DFT, of course, we propose a monodecarbonisation as in the literature we can see. For the moment, we don't know if it is really a mononuclear ruthenium like this, or there is something always with a dimer or trimer. Really, we don't know the species that we have. And for the smaller tests that we done in a stoichiometric at the beginning, we never see the ruthenium hydride. We see something at -5, 10 ppm, but we are not really sure that it is this ruthenium hydride. Yes.
Just one quick question.
Okay.
Julie,
oui.
I have a question. Is there any opportunity to apply catalytic reaction to functionalize the C4 position?
Yeah, in the C4 position, there is a lot of, not a lot, there is some example of the C4 functionalization in the C4 position with catalytic, with palladium. So for the moment, we never use this strategy. At the beginning, we wanted just to deblock the functionalization of the C3. Now we wanted to deblock the C3 and the C4 because the C5 is already known. So we will see, but there is a lot of examples.
Yes. So, dear Julie, it's time now to receive the Jean Normand Award 2020. So it's a prize for young associate professor who is working in France and is in less than 8 years in his career. So congratulations of all the new member and former member of the DCO, and congratulations for all the work you have already carried out. Merci.
Please, I want, of course, to say thank you to all the speakers from the first morning session. Please join me to thank them for to do the lunch break. Please take care that we want to start the session again at 14:30, very punctually, so please come back. And you have been given some small papers for these sanitary pass. Please bring it with you so that we can enter very fast into the room again. Thank you for your attention. Have a nice break and see you very soon. Bye.
J'ai pas le micro encore. Si, ça va.
Okay, so good afternoon, everyone. Thank you for being back here on time. So my name is Frédéric Lamati from the Institute Max Mousseron of Biomolecules in Montpellier. I'm chairing this session, this first session of the afternoon. And we will start this afternoon by the presentation of Sophie Feuillastre, who was awarded the Prix Émergence Marc Julia. I will say a few words about her career. She was awarded an engineering degree in chemistry from the School of Chemistry in Lyon, together with a master from the same university. And then she went on with studies in chemistry, doing a PhD with Olivier Pivat. And she worked on the total synthesis of valuable organic molecules. And this was completed in 2014. Then she pursued her work as a postdoctoral trainee at the CEA in the area of isotopic labeling and the design of molecules for energy application. She joined shortly a company in the same area, and then in 2016, she was hired by the CEA in the team of Gregory Peters. So I could say a few things on what she's working, but I'm not going to say actually anything because she's going to present us with what she's currently doing.
Thank you very much for the kind introduction, and thank you also for the prize, Marc Julien, and for letting me present my research work here. So I will speak about the research topic we perform at the CEA Saclay in the molecular labeling and bioorganic chemistry unit. And today, my talk will be about nanocatalyzed hydrogen isotope exchange. So in our lab, we are performing different research topics related to isotopic labeling. So the main part will be the development of new hydrogen isotope exchange methods. So that deals with the exchange of one hydrogen by one of its isotopes, so namely deuterium, which is the stable one, and tritium, which is the radioactive one. But also we have other thematics. For example, we perform the tritium labeling of bioactive molecules and nanomaterials. Here you can see one selected example. This is tritiated nanodiamond. So a nanodiamond can be used, for example, for bioapplication and drug vectorization. And it's important to have access to the tritiated one because the tritium will be a radioactive tag and you can follow in vivo the application of the nanodiamond. So those two are fundamental research topics, but we also deal with research with societal impact. So for example, we worked on ITER related fields. So ITER will be the new thermonuclear reactor. So it will deal with fusion and not fission anymore. And the fusion device will be using deuterium and tritium gas. The plasma generated will interact with one materials made of tungsten and beryllium, and that will create tritiated dust, a lot of tritiated dust. And that could create safety concerns, safety issues. So at the CEA, in fact, we synthesize relevant tritiated particles and do case studies on lungs, for example, or on GNO and cytotoxicity. Today, I will just talk about the development of hydrogen isotope exchange and start with the application. As you will see, deuterium and tritium compounds have a various and numerous field of application. The first one we can think about is the health sector, because we can encounter deuterium and tritium. With deuterium, you have the emergence of new drugs called deuterated or heavy drugs, which are drugs bearing one or more atoms of deuterium. You can also use them as mass standards, internal standards, and all omics, like metabolomics field. Tritium, as it's radioactive, you can use it as a tracer, so perform pharmacokinetic studies for drug candidates for the following inside the body: biodistribution, binding assay, or autoradiography, for example. But as chemists, we know deuterium for chemistry application and for mechanistic studies. Now there is new application for deuterium. Jeanne talked about it this morning, but we can use it also in OLED, in fluorophore, or with polymers. And you have also emerging fields, which are mainly imaging fields. So new imaging technique, which is DMI, deuterium metabolic imaging. Okay, so we know that there is a lot of application. Deuterium is very present in research and development, in drugs and materials, and that is, in fact, the fact that deuterium has a two-fold higher mass than hydrogen, leading that the CD bonds will be stronger than the CH bond. This is the kinetic isotope effect, and that is very interesting in either drug metabolism and in device lifetime. Why? Because if you carefully select the hydrogen, the CH bond you want to replace by a CD bond, for drug metabolism, you can slow down oxidative and racemization processes. And for device, you can slow down the degradation processes. That's why deuterated compounds are used. And know how to gain access to those compounds. So you can, as chemists, think about the most known method, which is a multi-step pathway. So you start from a labeled precursor, you redo your synthesis, and you will gain access to the labeled target. This is a very powerful way of doing it, because at the end, you will have a selective incorporation because you use the precursor, which is deuterium, and you will have a very high isotopic enrichment. Isotopic enrichment means that you will have replaced 100% of the hydrogen you want by 100% of the deuterium atom. Okay, but there are drawbacks. And the drawbacks are it's very time, resource consuming, and also waste generating, which is not possible when we use radioactivity. So we need to find another way of doing it. And the way we are studying at the CEA is the hydrogen isotope exchange. With this way, in fact, you just take your final compound and need the starting material. And you exchange selectively, which is a challenge, but you exchange an hydrogen by deuterium. The challenge is how to discriminate one hydrogen for another one, which they are very similar in terms of reactivity. And also another challenge is to gain access to 100% replacement of hydrogen by deuterium atom. But it's a very convenient way because it's a one-step synthesis. So for doing hydrogen isotope exchange, you will think about catalysis. The first catalysis, you can use it acid-base mediated catalysis using either acid, Lewis and Bronsted acid or bases. But at the laboratory, we deal with metal catalyzed hydrogen isotope exchange. So with that, you can think about classic catalysis like heterogeneous or homogeneous. They are very complementary. They have benefits and drawbacks. For example, for heterogeneous catalysis, you will have a maximized isotope incorporation. You use very simple and commercial catalyst, and it's an easy workup. But the drawbacks are the chemo and regio selectivities. And if you think about homogeneous catalysis, it's the contrary. So at the lab, we are thinking about in-between catalysis, which is nanocatalysis, which combine the benefits, but also there is some drawbacks. Like, for example, sometimes the catalyst may be difficult to access and it's expensive. So the journey in the isotope exchange world starts with a collaboration with Dr. Bruno Chaudret at Toulouse. In fact, in his lab, they synthesize nanoparticles and they synthesize ruthenium nanocatalysts. So simply starting from this precursor, you will decompose and you will generate the nanoparticles under hydrogen atmosphere, and you will stabilize it either using a stabilizer like a polymeric matrix or using ligands. When they use, in fact, amine ligands and put it under a deuterium atmosphere, they noticed that there was an exchange from hydrogen isotope to deuterium atoms at the alpha position of the nitrogen. So that was the beginning. And at this time, a new postdoc named now Gregory Peters, and now it's the team leader, start the work on the field of the labeling of ASA compounds and using very model substrates, simple amines like aliphatic or aromatic like quinoline, pyridine, or indole, using mild condition, 20 to 55 degrees and a broad scope of solvent, he succeeds to label at the alpha position or beta position. How to explain the regioselectivity? For that, they performed DFT calculation with the team of Romuald de Poto, and we can explain, in fact, the selectivity by this calculation. So in fact, you have the nanoparticles, and the first step is a nitrogen coordination to the particle, and you will have also with a second ruthenium atom an agostic interaction. Then you will have the CH activation step. You will have a 4-member dimethyl cycle. You will have an HD exchange by deuteride diffusion, and you will have reductive elimination. So that explains the alpha selectivity. Okay, but for beta selectivity, in fact, starts the same. So you will have the nitrogen coordination, agostic interaction. And if you want, you can also use base to have the NH activation. And after the same, it's not a 4-member, but a 5-member there, dimethyl cycle, HD exchange, reductive elimination, and you have the beta position. And with that, we have a scope of amine for the beginning. After, we push forward for the labeling of other derivative and heterocycles of interest like oxazole, imidazole, benzoderivative, triazole, and we explain the selectivity using DFT calculation. So as you can see, we can explain the alpha, beta, and gamma position with this type of metallocycles, so either dimetallic cycles or simple metallocycles. So to conclude with the beginning of the work, in fact, they applied it to very simple substrate, but also on more challenging and bioactive compounds like paroxetine, suvorexant. So the method has a broad substrate scope. So you can label many biologically relevant functionalities under mild reaction condition, use it broad range of solvent. We can explain this regioselectivity with high deuterium atoms incorporation. And then we were wondering that as we have a 4-member and rigid metallocycle, can we reach the enantiospecific exchange? And the answer, as you can see here, is yes. So we start with amino acid, and the reaction is in fact fully enantiospecific. You have a good deuterium incorporation, as you can see here, and the non-racemization process is explained by this dimethyl cycle, which is rigid. And that was applied for various important number of amino acids, but also on peptide derivatives. After, we try also to apply the method to other substrate of interest. This is for pharmaceutical industry, those ones, which are DNA, RNA bases, and related drugs labeling. So we start with purine derivatives, so adenine and guanine substructures. And as you can see, using mild reaction condition with various solvents, we have a good incorporation of deuterium atom. But for some of them, like idilalizib, you can see that the incorporation is not so good and we can increase it. So with that idea in mind, we start to do nanoparticles engineering. how to do so. In fact, you can change, as I showed before, the stabilizer, and we start to being interested in all the type of ligands which are N-heterocycles. So depending the heterocycles you choose, you can have different type of properties. So you can have organosolubility, water solubility, you can enhance the solubility, in fact. So remember idealism, when we use the one stabilized by NHC, we go from 80% of exchange to 97%. And then synthesizing water-soluble nanoparticles, we succeed in labeling complex structures like oligonucleotides because they are only soluble in water, so we need water solubility. And as you can see, after one run of catalysis, we can incorporate more than 3 deuterium atoms, and after 3 runs, more than 5 deuterium atoms that could be used for development of new drug candidates as a mass standard, for example. And that was applied to more complex structure like a 12-mer oligonucleotide. So to conclude on ruthenium nanocatalysts, we succeed in labeling both sp3H and sp2H bonds with good regioselectivity and cooperation. So you can see here amino acid and thioethers also. But there are drawbacks, and the main one was the reduction. Sometimes when we use easily reducible functions like aromatic rings, unsaturated bonds, heterocycles, we see that we reduce instead of label. So for that, we think about catalyst engineering, use also other metallic particles, and use a new type of chemistry, which is flow chemistry. And flow chemistry is also of great interest when you try to maximize the enrichment, because depending the application, you will need the 99% of incorporation. Okay, so start with the catalyst engineering. We'll have a look on this publication of the Glorious group and see that it takes heterogeneous catalyst and it can switch the reactivity by adding N-heterocycles. N-heterocyclic carbene, sorry. So that was applied in the context of reduction and in the context of coupling reaction. Okay, so the idea was, can we do it for labeling? So in fact, we prepare ruthenium on carbon modified catalyst by adding ligands. So you can see here the NHC we choose, and depending the amount, we can have different type of selectivity. Results are shown here. When we try to label a new type of compound with our alcohol, in fact, using the nanoparticles engineering, you can improve the regioselectivity. For example, when we use ruthenium on carbon, we have 3 positions here. And with the engineered nanocatalyst, in fact, you have just the position alpha. So we gain in regioselectivity. But the most interesting part was the switch of reactivity between the labeling and the reductive deuteration. For example, for quinoline, which is an easily reducible function, using ruthenium on carbon, you only reduce the compound and did not succeed in recovering the label one. Using the modified catalyst, which is the blue here, you can see that you have the labeling and you reduce the amount of reduced compound. And that is explained, in fact, by the incorporation of bulky ligands around the catalytic surface. So you will prevent the pi coordination, which is responsible for the reductive deuteration, and you will favor the N coordination responsible for the deuteration process. We switch also the metal, as I said, and we switch from ruthenium to iridium because iridium is well known as, for example, with the Crabtree catalyst for hydrogenation, but also for labeling with Crabtree and Kerr teams. So we synthesize the nanoparticles with iridium and with NHC. And as you can see, we can label aniline. Okay, but this is good, but in fact, we think that synthesizing nanoparticles require sometimes specific skills and specific equipment, especially if they are not hair stable. For example, you need a glove box. So we think that can we make it more simple, more practically simple? And the answer, in fact, is yes. We simply use the precursor we use for the synthesis of the nanoparticle, you can see here. And in fact, we put it in the mixture with the molecule we want to label under the condition, mild condition. And we observe that we recover the molecule and we have the label one, and we generate, in fact, in situ, iridium nanoparticles and also iridium complexes, meaning homogeneous catalysts. So this is interesting because you will have a combination of homogeneous catalysis and nanocatalysis. And that will lead to multiple DT incorporation with no reduction, and it's a practically simple method. But with iridium, it's limited to CSP2H process. So it's great, but we want also CSP3. So for that, which we switch again, and we create rhodium nanoparticle in situ once. And as you can see, we succeed in labeling both SP2 and SP3H bound, labeling of N heterocycle. Okay, I can hear me, it's fine. So labeling N heterocycle and alkylamine, benzylic scaffold under mild reaction condition. If there is a reduction process, we use additive to prevent it. You have a high functional group tolerance. It's a practically simple method, and you will have multiple DT incorporation. And as I said, we start also to switch the type of chemistry from batch to flow. And why flow? Because in fact, we are looking for particular selectivities and maximize isotopic enrichment. And in fact, flow chemistry has a lot of benefits. For us, it was the efficient fast mixing between gas, liquid, and solid. It was our case. You have also easier and faster procedures. You have the recyclability of the catalyst and the safe handling of gas. And because we believe so hard in flow chemistry, we apply for a European project, which was financed and start the 1st of January 2020. The project is FLIX for flow isotopic exchange and gathering 5 European countries and industrial and academic partners. And the first result we have in this project is we start to study the labeling versus reductive deuteration process. So we start with the quinoline model because, as you have seen, it's very easily reducible. And in flow conditions, so using the H-cube apparatus, you can see that we can succeed in incorporating deuterium, but with moderate incorporation, and we have the reduced compound also. So the aim was to favor the labeling, reduce the reduction, and for that, we change the substrate concentration, we decrease the catalyst loading, we perform so optimization, and the result of the scope, I can show you is this one. So for quinoline, we succeed in improving the incorporation, reducing a little bit the reduction, but the most important thing, if you look for the example for pentoxyphylline, aldehyde, you can see that when you use batch condition, you will have only reduced compound. With flow chemistry and the optimized condition, you can have the level 1. So this is the first step. Also, with flow chemistry, we want selectivity and we want 99% of incorporation for deuterium atoms. So we use the scope of deuterated aliphatic amines because they are useful for material purposes. And if you look at the first result, which is batch versus flow with pyrrolidine, with batch reaction, you can label the compound, but you will have no selectivity and you will reach a plateau. Even if you perform runs and runs, it will be really difficult to improve the labeling. With flow reaction, using 4 iterative runs, it's approximately 20-30 minutes of reaction. You will have the selectivity and you will have the maximized isotopic enrichment. Also, which is interesting in flow, you can play with flow. You can play flow versus flow system, meaning that you can do a single pass. You have the entrance, you have the exit, and you do only one run. Or you can do iterative run and performing iterative cycles. So for example, one run, you have this position labeled at 99%. If you continue, you will gain access to this position also. So regarding the scope for the little mean part, you will see that you have selectivity and you have also a good to excellent isotopic enrichment. So now I will just do a brief focus about tritium because it's not so common to use radioactivity. So at the lab, we deal with tritium labeling. So tritium, it's the radioactive isotope. It's a beta emitter, meaning that you have risk with contamination, but no irradiation. It's not plutonium. The half-life is 12 years. So this is my last slide. First of all, I prize for here. I will think my team, the prize students I am looking to work with. So thank you, Etienne, Kevin, thank you. Sébastien Garcia-Aragon, the MacGyver engineer of the lab. All the collaborators, so European projects.
So,
reach using the flow, does it mean that, of course, the time contact is very important? You have a sort of passivation of your nanoparticles. How do you explain?
In fact, yeah, the contact is very different because with flow chemistry, you deal with residence time. So the compounds do not spend so much time with the catalyst. At the time it's in the cartridge with the catalyst, you have a huge amount of catalyst and just a small amount of compound. And in fact, to just favor the most sterically favored position, in fact, that could explain the selectivity.
Thank you.
Any other questions? So before thanking again Sophie, I have the pleasure to, on behalf of the Organic Chemistry Division and the French Chemical Society, to so give you the award for the Marc Julien. As if I didn't know about Marc Julien. So actually, actually, I mean, of course, I knew him personally. I'm sure he would have been really interested in what you're doing, because it's really interesting, this mix of organic molecules and nanoparticles and deuterium and labeling. So congratulations for your good work. So I have to say that this award is for a young researcher 6 years after completion of the PhD.
Thank you very much.
The next speaker is Charlotte LORTON. Okay, so Charlotte was awarded the Thesis Prize d'Inational, and just a few words about what she's been doing so far in chemistry. Completed her PhD last year under the supervision of Arnaud Voiturier at l'Institut de Chimie des Substances Naturelles à Gif-sur-Yvette, south of Paris, by developing methodology in asymmetric redox organocatalysis using phosphates. So after this PhD, she moved recently to Liverpool in the UK, and she's currently working under the guidance of John Bauer, and she's working on a new chiral gold complexes. So she's going to present us today with the work she's been doing during her practices. Charlotte, the floor is yours.
Thank you. So good morning, everyone. First of all, I would like to thank the Division de Chimie. So good morning, everyone. First of all, I would like to thank the Division de Chimie Organique for organizing this day and for giving me the opportunity to present you my work. So today I'm going to present you my PhD work based on the development of new methodologies in asymmetric phosphine redox organocatalysis. So this work has been done under the supervision of Arnaud Voiturier at Institut de Chimie des Substances Naturelles in Gif-sur-Yvette. So phosphines play a key role as stoichiometric reagent in a lot of reactions in which they are oxidized, such as the Wittig reaction, Mitsunobu, Staudinger, or Apple. All of these transformations are very efficient and daily used both in industry or in academic laboratories. Unfortunately, their major drawback is the concomitant formation of a stoichiometric amount of phosphine oxide as waste that makes this reaction not eco-compatible at all. To overcome this issue, it has been proposed to make the reaction catalytic in phosphine. In other words, it has been proposed to reduce the phosphine from the phosphine oxide thanks to the use of a reducing agent. This strategy has been initiated by the development of the first catalytic Wittig reaction developed by O'Brien and co-workers in 2009. In this transformation, several alkene derivatives could be obtained with quite good yields, starting from only 10% of phospholan as catalyst and D-phenylsilane as a reducing agent. So through this strategy, it seems that several parameters must be controlled for the development of P3, P5 redoxyl transformations. The first parameters concerns the nature of the catalyst, because the phosphine oxide must be easily reduced, knowing that cyclic phosphine oxide are easily reduced than the non-cyclic ones. And it's especially true for the cyclic phosphine oxide with 4-member ring than 6-member ring. In other hand, the phosphine must be nucleophilic enough, knowing that cyclic phosphine with 6-member ring are more nucleophilic than the 4-member ring. So the best compromise between the reduction and the nucleophilicity has been found with cyclic phosphine with 5-member rings, such as the phospholan or the phospholine. The second parameter concerns the nature of the reducing agent, because this one must chemoselectivity reduce the PO bond, which is one of the strongest bonds in organic chemistry. Organosilanes meet perfect criteria, such as the phenylsilane, the diphenylsilane, or PMHS and TMDS. Finally, the reaction conditions also have a crucial importance, and it's possible to add some additives in order to facilitate the reduction of the phosphine, such as this phosphate, which has been first used in 2012 by Beller and co-workers. So keeping in mind those parameters, several other P3, P5 redox cycling transformation has been developed. For example, the first catalytic Mitsunobu reaction has been patented by O'Brien and co-workers and then published in 2015 by Aldrich and co-workers. In this strategy, 10% of phosphoran has been used as catalyst associated with phenylsilane as reducing agent. The first catalytic Staudinger reduction has been developed in 2012 by Van Def and co-workers, with here the dibenzophosphol as catalyst and the phenylsilane as reducing agent. More recently, the first catalytic tandem reaction, Michael addition Wittig reaction, has been developed in my PhD laboratory. So starting from indole 2-carbaldehyde and dialkyl acetylene dicarboxylate, several pyrroloindole could be obtained with quite good yields. In this strategy, 5% of phospholine has been used as catalyst with a reduction system phenylsilane phosphate. So in this context, the first aim of my thesis was to extend this catalytic tandem methodology to the use of alinoates. So the reaction begins with a nucleophilic addition of the phosphine on the alinoate to generate a zwitterionic species. This one reacts with a substrate through an acid-base reaction to create a nucleophile. So this nucleophile reacts with the vinyl phosphomer through a nucleophilic addition, followed by the intramolecular Wittig reaction and then the isomerization as last step to obtain the target compound. So this reaction was totally unknown, so we had to optimize all of the parameters of this process. Unfortunately, even after an extensive optimization, the best yield doesn't exceed 18%. So this quite poor yield can be explained by a side reaction of reduction of alinoates. So this reaction is very interesting because it represents the first example of organ catalytic semi-hydrogenation of alinoates. But in the context of the development of new catalytic tandem reaction, it highlights the difficulty to use alinoates associated with phenylsilane. So in second time, the reaction has been re-optimized here with one equivalent of triphenylphosphine to obtain 80% yield after 3 hours in a microwave reactor. So keeping those best conditions, the scope of this process has been studied. We can notice that the position 5 on the substrate and the position 6 are well tolerated, unlike the position 7, and with a methyl in position 3 on the substrate, 51% of yield could be obtained. So in conclusion of this first part, the first tandem reaction starting from alinoates has been developed for the synthesis of 18 examples of pyrroloindole with yields between 32 and 88%. Moreover, thanks to this first study, it appeared to be difficult to use alinoates associated with phenylsilane. So to complete the second aim of the thesis regarding the development of new catalytic tandem reaction, it has been decided to come back to the substrate historically used in the laboratory, namely the dialkyl acetylene dicarboxylate reagent. So first of all, the tandem reaction depicted here has been investigated for the synthesis of 2,5-dihydropyrrole derivative. After an optimization, 5 different functional groups had been studied in those conditions with very heterogeneous yields between 6 and 99% in the presence of a carboxylenzyl, starting from 10% of catalyst. Unfortunately, for the synthesis of those two compounds, no reaction has been detected. That can be explained by the presence of a side product, namely the pyrrole. So due to the presence of this pyrrole, it has been decided to put this reaction aside and to focus on the second tandem reaction shown here for the synthesis of tetrahydropyridates. Here, 9 functional groups has been investigated with yields up to 92%, starting from 10% of phospholate and 2 equivalent of penicillin in toluene at 60 degrees Celsius overhead. In the other hand, we can notice that during this process, a quaternary center is created. So we wonder if it would be possible to use a chiral phosphine in this transformation and thus to develop the first catalytic and asymmetric tandem reaction. So this third is the most challenging one. Because at the beginning of the thesis, there was only one example in the literature concerning the first catalytic and asymmetric integration developed by Werner and co-workers in 2014. In this strategy, a very good enantioselectivity could be obtained with 90% EE, but we can notice that the NMR yield doesn't exceed the catalyst loading. So it seems to be complicated to have both good yields and good enantioselectivity in a P3, P5 hydroxyapine transformations. To know if it will be the case in our tandem reaction, several chiral phosphine have been investigated for the synthesis of chiral 2,5-dihydropyrols. The best enantiomeric excess is 82%, but associated with only 40% yield. And if this yield is increased to 51%, the enantioselectivity drops to 22%. About the synthesis of tetrahydropyridine derivative, the best enantiomeric excess is 31%, associated to an interesting 73%. But here again, when the yield is increased to 95%, the enantioselectivity drops to 16%. So it seems to be complicated to have both goodies and a good enantioselectivity with those two tandem reactions. So thanks to this disappointing analysis, it has been decided to turn our intention to the substrate shown here. So this substrate has been first used in a tandem reaction by Yavari and co-workers in 2004. So starting from 1 equivalent of 3-phenylphosphine, 5 examples of cyclobutane derivatives could be obtained with yield between 77 and 88%. So the reaction begins with a traditional nucleophilic addition of the phosphine on the dialkyl acetylene decarboxylate reagent to obtain the zwitterionic species, followed by the acid-base reaction, the Michael addition, and the Wittig reaction to obtain the target compound. So we wondered if it would be possible to use a chiral phosphine in this transformation, and thus to develop the first catalytic and asymmetric tandem reaction. Towards this aim, several chiral phosphine have been used in this process with a 70% EE as best enantiomeric excess in the presence of the diethyl PPE chiral phosphine, but here again associated with only 45%. So in a second time, the Wifos chiral phosphine have also been tested in this transformation. And for the first time, we could obtain both good yields and enantioselectivity up to 90% EE in the presence of this chiral phosphine. So this best chiral phosphine has been kept to study the scope of this process. And we can notice that whatever the position or whatever the electronic properties of the substituent or whatever the steric hindrance, the outcomes of this process are not affected by that. The reaction can also be performed in the presence of disubstituted aryl, heterocycles, naphthyl, and aliphatic ketones. Later, the reaction has been extended to the use of cyclic substrate in order to obtain a spirocyclobutane derivative with an interesting quaternary center. But however, due to the presence of this pyrenic center, we can notice that the yields are lower than the previous one, while the enantiomer selectivity remains quite good, up to 91% E for the synthesis of these compounds. Finally, the efficiency of this process has been proven by with the scale-up. So it's now possible to access to 1 gram of chiral cyclobutane derivative with 99% yield and 90% EE, starting from only 23 milligrams of chiral phosphate. And after post-hydrogenation, it's also possible to access to cyclobutane derivatives with a 66% yield. So in conclusion, the first catalytic and highly enantiomer selectivity tandem reaction has been developed for the synthesis of 28 examples of cyclobutanes in one head and 6 examples of cyclobutanes in other head. Later, this reaction has been extended to the use of ketoester to add more examples. So to summarize this presentation, the first tandem reaction between an indole carbaldehyde and alinoate has been developed for the synthesis of pyrrole wonder, while 2 new catalytic tandem reactions have been studied for the synthesis of heterocycles. And now it's possible to access to chiral cyclobutane derivative through a P3-P5 redox cycling transformation. I would like to thank all of the staff members of ICSN, especially my team phosphorus chemistry and catalysis, and of course my supervisor Henri, all of the common services, the LMR, HPLC mass, and crystallography for their help, and all of you for your attention.
Thank you very much, Charlotte, for your very nice talk. So due to time constraint, we can have one question. So anyone who wants to ask a question to Charlotte? This is the famous one question effect. There was one in chat? Okay.
Armel Palancian ask you, Charlotte, very nice work. For the reaction of indole carboxylaldehyde with alinoate, did you try to replace alinoate to alkenoate to minimize the amount of semi-hydrogenation?
You mean with a terminal alkyne?
I presume you say to replace alinoate by alkenoate, considering that alkenoate can serve as masked alinoate.
Yeah, it can be a possibility because after the nucleophilic addition of the alkenoate, we have exactly the same spherionic species, so it can be a solution.
Thank you very much, Charlotte. So you're awarded today with the Dina Surdin PhD Award. So this is an award which is funded by a foundation, the Dina Surdin Foundation. And so I will read a few words about this foundation, which is funding the award. And I apologize for those who don't understand, but it will be in French. This goes with the award. So, après avoir obtenu une maîtrise de chimie à l'Université d'Orsay Paris 11, Dina Surdin était entrée comme doctorante sur le campus du CNRS à Thiers, dans le groupe de recherche réactivité et mécanismes en chimie organique, alors dirigé par Madame Choubard, directeur de recherche au CNRS. Son travail fut récompensé par l'obtention du titre de docteur de 3e cycle en 1974. À cette époque, déjà, les recrutements dans les organismes de recherche publics étaient difficiles. Espérant tout de même continuer à travailler dans un laboratoire de recherche, elle remplace pendant 2 ans au laboratoire d'enzymologie du CNRS à Gif-sur-Yvette un ingénieur ayant pris un congé pour convenance personnelle. Après ce stage, ne trouvant toujours pas de poste stable dans un laboratoire de recherche, elle décide de changer d'orientation. Elle s'inscrit à un stage de reconversion afin d'obtenir un diplôme d'animateur et conseiller d'entreprise. C'est au cours d'une mission durant ce stage qu'elle disparaît dans un accident de la circulation. À ce moment-là, en 1977, ses parents, M. et Mme Surdin, décident de créer la fondation Dina Surdin à la mémoire de leur fille. Alors, cette fondation a créé au sein de la Fondation de France, a été créée au sein de la Fondation de France, qui gère le patrimoine de la Fondation Dina Surdin. Sa famille, qui avait vécu avec Dina les difficultés qu'elle avait rencontrées, a donc fixé comme but à la Fondation d'apporter une aide à de jeunes chercheurs. Donc, une des actions actuelles de la Fondation, c'est de remettre 2 prix. Ces prix sont annuels et les lauréats de ces prix sont choisis, l'un par la Division de Chimie Organique de la Société chimique de France, l'autre par la Société française de biologie, de biochimie et de biologie moléculaire. Il faut noter que le conseil d'administration de la Fondation Dina Surdin n'est pas intervenu dans le choix de l'allocataire de la bourse de thèse et n'est jamais intervenu dans le choix des lauréats des prix de la Fondation Dina Surdin. So today, this is the division of the organic division, organic chemistry division of the French Chemical Society, which I decided to award you with this thesis prize. So the Dina Surdin Award Thesis Prize. So, thank you. So now we will keep going on the program with an oral communication. So this oral communication is going to be presented by GRAMAGE-DORIA from the Institut de Chimie de Rennes. And I will encourage the people here in the audience, if you know some people who would be willing to present their work, so young permanent researchers such as Raphael, to present their work at such an occasion, don't hesitate. When we organize those days, we are asking people to apply for oral communication, and don't hesitate, because I think it's really a great opportunity for them to be able to present this work. So without taking more time from Raphael, I give you the floor.
Thank you, Frederic. And thank you also the whole organizers of the SFC DCO division for giving the opportunity to me to share with you some of the results that we are doing in the laboratory in the Institute of Chemical Sciences of Rennes. So one part of the research we are doing is much, let's say, inspired by the action mode of enzymes. So we have seen many beautiful and excellent catalysts this morning and this afternoon. And if we look at these enzyme catalysts, which we find in nature, they are extremely active and selective. And the action mode, why these catalysts are so active, so powerful, is because they use a completely different type of toolbox that we use in small catalysts, either organic or transitional metal-based. So we know that enzymes are able to destabilize the ground state. They are able to stabilize the transition state. They have a very high specificity for substrates. And this is what I try to show you here. So this is an enzyme, and this is the active site we have really inside, deep in the pocket of the enzymes. And this type of enzymes, for instance, they stabilize the substrates, and they are typically very good to resemble, let's say, the transition state. And this is because mainly they have a huge variety of weak interactions near to the active site, let's say in the second coordination sphere, where the reaction occurs, to stabilize this type of intermediates. For instance, this is particularly relevant for substrate distortion. And if we look at the different type of weak interactions that have been utilized in transitional metal catalysis to pre-organize substrates, this is of course a long history. And we can go back to the time of Breslow chemistry, where he used the hydrophobic effect to pre-organize substrates for oxidation chemistry. And I pick up this very nice example from Krapke and Bradvik in 2006, where they have this dimanganese oxide species. So this is the active site, and is appended in the second coordination sphere with a hydrogen bonding made by carboxylic acids that are able to pre-organize a substrate in such a way that only this benzoylic position is selectively oxidized. If you don't have this substrate recognition site in the second coordination sphere, you will end up with a mixture of oxidized compounds in many, many positions. So this is really an interesting feature that we can eventually implement in other types of transitional metal catalysts. There is a lot of research dealing with substrate pre-organization in metal catalysis. Many reviews and even written books have appeared on this topic. So in the lab, we thought, okay, can we eventually look at a different type of weak interaction to be used in transitional metal catalysis? And if you look in the literature, a lot of people use hydrogen bonding, because this is very unidirectional and interesting. You can use different type of, even different number of hydrogen bonds at the same time, ion pair. But we look at something different. We look at these nitrogen-zinc interactions, okay? This is pioneering work from the Sanders group, where they use this type of tricyclic zinc porphyrins that behave as nanoreactors. This is chemistry done in the 90s. And they managed to pre-organize these pyridinic substrates to promote the Diels-Alder reaction, and they have switching the selectivity. The end product that you will classically form is not formed. They do form this exo adduct. So this is very interesting. This type of nitrogen-zinc interaction is basically kinetically labile. So this is dynamic in nature. And we wanted to exploit this type of interaction in transitional metal catalysis, which has been really never studied. And as a really proof of concept, we pick up different type of zinc-containing building blocks, such as this zinc porphyrin or zinc sulfates that are very easy to synthesize in a gram scale in the laboratory. And we use representative allo-substituted pyridines that are able to interact with this type of zinc building blocks. And then a trivial palladium catalyst can perform eventually a Mizrachi Heck reaction. And because this interaction is non-covalent in nature, you can go back, liberate the zinc building block, and form your compound. So in the second coordination sphere, you can eventually control in a remote fashion some type of transition metal catalyst. And this was applied, for instance, for this Mizrachi Heck reaction, where you use a conventional palladium triphenyl phosphine catalyst, in which does not work under these conditions that you can see here for different type of allopyridines. And as soon as you start to introduce to your reaction mixture zinc porphyrin, you start to have some reactivity because you block the pyridine and you prevent formation of undesired species. And if you introduce zinc sulfate blocks to the catalysis, the reaction is even increased, works much better. And this is because these zinc sulfates building blocks interact with your pyridine substrate much stronger. But of course, this is not nice in a way that you need to use at least stoichiometric amounts of this type of compounds. And although you can recover them at the end of the reaction, we thought that perhaps it should be interesting to look at the really truly catalytic version, in which you build up metalloporphyrin here, appended with nitrile groups that are well known in the literature to bind to palladium, for instance, as an active site. So in the same ligand, you incorporate your substrate recognition site and your active site. And I will not go into details, but we managed to introduce different type of metals inside of the porphyrins that you can play with the association constants of these porphyrins with the pyridines. And in a representative Suzuki-Miura reaction for this particular type of substrate, you have a very nice reactivity using this time only catalytic amounts of this type of ligand. So this basically shows how really unique it is, this type of zinc interaction with pyridine. And we wanted to go a little bit further and look at the really more challenging, let's say, CH bond functionalization of pyridines. This is a really interesting and challenging topic, because what happens, and this has been well studied, Hardwick is really the pioneer of this type of chemistry. This type of borylation chemistry using iridium catalysts represents a major issue. Typically, these reactions are done under aliphatic conditions, and we would using aliphatic solvents because you need a solvent that is not reactive. What they found out is that this type of N-chelating ligands, actually, that are somehow active for this type of borylation chemistry, what they realized is that they form this type of resting state in which the pyridine here binds to your active site. So basically, if you want to have an active borylating catalyst, what you need to find out is a system that is unable to form this type of resting state and form other intermediates in the catalytic cycle as a resting state. In 2019, Nakao developed this type of ligand after extensive screening of ligand modification and fine-tuning of the ligand. And so they appended this type of phenanthroline with a boryl-containing substituent that is able to interact with zinc, and then they have borylation in the meta position, but it only works if you have this ortho-substitution pattern that avoids this famous resting state. So we thought, okay, can we apply with our approach a solution to get selective borylation of pyridines? And by molecular mechanics, we basically designed this type of zinc porphyrin appended with an NN chelating ligand that in principle should be able to place an iridium here and is in a good distance to get metaborylation of pyridine. So here the substrate recognition site by zinc is 10 chemical bonds apart from the active site. And this work has been mainly done by Paolo, who was a postdoc and initiated this project, and Jonathan, who has been really most of this chemistry that I'm showing you today. So they synthesized in 4 or 5 steps this type of ligand, and they managed to prove and demonstrate that although it looks highly constrained, it is able, because you have some certain flexibility around this carbon-carbon bond here, is able to accommodate pyridines. As you can see here, we calculate this type of binding constant, which is higher than 10 to the 4. And this 10 to the 4 association binding constant between the substrate and the substrate recognition site is something comparable that you can find in some enzymes that bind substrates. And this is easily measured by UV titrations. And this is also very easy to see by NMR spectroscopy, because then you have these ortho-meta paraprotons of pyridine that are upfield shifted, as you can see here. So they do not appear in the aromatic area, but more to downfield shift fields. They even managed to get X-ray structure to have an idea how our supramolecular ligands are able to bind this type of nitrogen-containing heterocycles. So here you can see that the pyridine actually binds as we expected to the zinc here. And what is nice is that it binds in the same phase where you would expect to have your active iridium site here. And you can see that if your iridium center is here, this CH in meta is going to be really, really close. So with this idea, we try also to have some increased level, let's say, of reactivity prediction for this type of CH bond functionalizations that sometimes are really based on trivial and random screening of conditions. And the same occurs for this type of imidazole substituent in which the beta position, beta hydrogen here, is really close to where you expect to introduce your active site. So we performed this type of borylation chemistry with pyridines, and we got 90% selectivity towards the metaborylated pyridine. And the isolated yield is a little bit low because we do the reaction in small scale, and purification is not easy, but you can scale up the reaction. You have very nice yields. And what is interesting is that we have not detectable traces amount of ortho or para-selectivity. So it's really extremely selective system. You can see what happens if you don't have a porphyrin in the second coordination sphere. You end up with a mixture of meta and para-borylated product in a statistical ratio. It was known by Henri and colleagues in Japan. You can increase the ratio of iridium and ligand, and you can get bisborylation this time without any detectable traces of ortho or para-borylation. What is interesting is that we are able to perform this type of reaction in non-aliphatic solvents. And this is really important because we increase the solubility of our system. We use a polar non-coordinating solvent that maximizes the interaction between the zinc and the nitrogen of the pyridine. And this was really unexpected because you will see in the literature is that if you want to borylate benzene, this is much easier to perform the fully aliphatic versions. So, but in our case, it's the opposite. And so we even have traces of borylation of toluene. We calculate the selectivity of the system, and we are almost 400 selectivity of pyridine per toluene. And this is basically impossible to reach with conventional catalysts. We studied some substrate scope, and it showed very nice compatibility with different types of functional groups that will not go into details because of the time, I guess. Also for the kinetic, I didn't plot all the data, but the reactions show that this is first order in pyridine, and this is the opposite what Harvey found. It was zero order impurity. And so what basically indicates is that this type of supramolecular ligand behaves as if the pyridine is non-heteromagnetic. The reaction is zero order in B2P2, as we can expect, first order in iridium, as we can expect. And what is interesting here is that we don't have product inhibition. So this suggests that once the product is formed, it is released from the pocket of the catalysts. Although we have some catalyst deactivation because at the end it degrades. We did some Michaelis Menten studies and it plot the reaction was very nice. So basically it showed that the reaction follows the Michaelis Menten rate law equations. This is typically behavior you encounter in enzymes. This is the mechanism that we came up, and this is not postulated or calculated mechanism. This is some of the intermediate we were able to identify by enema, because basically the substrate that binds to your pocket has specific chemical shifts that you can follow in the NMR, something that you cannot do with other type of systems. So basically you have substrate binding, CH activation here, then borylation, and then product release, and then reactivation of the catalyst. So in this type of system, we have the resting state at this position here. We have very nice substrate selectivity. You can use a mixture of all isomers of methylpyridine. Together, you can form up to 10 different compounds regarding the region, the site selectivity. You form only one of those selectively. So this is really unique substrate specificity. You can also use this type of approach for temporal control of reactivity. You take a compound that does not work because it does not bind to the pocket, and then you put a base. After 3 hours, the substrate goes to the pocket, and you have a boost of reactivity. So again, these features that are more or less similar to enzymes at some point are something that you cannot find with classical first coordination sphere chemistry. I would like to finish. Thank you, the different funding agencies, especially the ANR. And lastly, small announcement, please come and participate in April next year in Rennes. We have very nice international symposium on catalysis. Send your abstracts by 15 February. We have very nice European international speakers. Thank you for your attention.
Thank you very much, Rafael, for this very nice presentation. So we have time for one question. On the chat, I don't know if there are any. No. Vincent?
Do you think that in your case, the pyridine is activated only by the activation of the porphyrin, or is the porphyrin zinc is also playing the role to decrease the electron density of the pyridine and then make your CH bond also much more acidic?
Yeah, this is a very excellent point that we think about that, and we don't have any answer to that, but we expect to have an answer in the future. Thank you.
Okay, let's thank again Rafael. So the last presentation of this afternoon is the awardee of the Jean-Pierre Sauvage Award. And this is Davide Odisio, who worked about his career. He got a Master of Pharmaceutical Chemistry from Torino in Italy. Came in 2007 to France for a PhD, which was awarded from the Université, what was called at that time Université Paris Sud, and worked under the supervision of Mouad Alami and Samir Messaoudi on the novel biocine derivative as inhibitors of HSP90. Then he went on with a postdoc at the Max Planck Institute in Mülheim with Nuno Molid, followed by a 2-year stay in industry with Eli Lilly in the UK, before joining the team of Frédéric Tarrant at CEA to work on mesoionic compounds, their click and release reactions with applications in biology. Since 2016, he's heading the CEA C14 labeling lab. And so I leave you the floor to present your work.
Thank you very much. So you can hear me. It is a real pleasure to be here today. And I would like to thank the DCO, the past bureau, the current one. It's for me a real honor to receive this award, but I need to say that this was a collective one. I had the chance to have great mentors over my career and a very smart group of people that I work with. So I would like to thank all of them for that. Well, before starting talking about carbon isotopes, I would like just to give a short introduction to the organization I work for. We have seen some CA people today over the day, so you may not know, especially abroad. So the CA is the French Atomic Energy Commission, and it is a government-funded research organization. We are located in Saclay, really close to Paris. So what's peculiar in the chemical department of CA is that we have facilities that can handle radioactive isotope and perform synthetic organic chemistry. So with the tritium, we have seen my colleague Sophie right before, and carbon-14 as well. So the radioisotope for hydrogen and carbon-12. So in this context, we are interested in developing new methodologies that allow to efficiently label molecule of interest, starting from the simplest starting material, hydrogen or CO2. And we try to get a higher efficiency and availability of the compound of interest, as well at the same time reducing the cost, the time, and the waste that are generated over the process. So in particular, my lab is dealing with carbon-14 radiolabeling. And you are all familiar with carbon-14 for radio dating. So this is something that's an excellent technology, but you may not know that C14 is also interested in a number of societal impacting aspects. Actually, this is a long-lived isotope, more than 5,000 years, and it emits a low energy radiation electrons, so beta minus radiation. So there are a number of advantages using carbon-14. There is a high sensitivity of detection thanks to the beta imaging, also autoradiography, for example. In addition, of course, when you modify an organic molecule by replacing carbon-12 with carbon-14, you do not change the structure, so you can track the molecule as it is. And finally, you have a reliable quantification without need for internal standards, for example, with mass technologies. So these aspects are of importance whenever you need to track an organic molecule. For example, this is a case for veterinary drug development or human food safety studies. But it's as well of interest for environmental fate studies for the development of a new pesticides, for example. And the most well-known is probably drug development. Actually, before a molecule reaches the market, there's a lot of studies behind that. And one point is that you need to know exactly the ADME properties of the compound, which is the absorption, their distribution, so the metabolism, and the excretion of the molecules. And so in this case, in particular for clinical development, C14 is still a gold standard technology. Well, this is all very nice. So what's the trick? What's the problem? Actually, this comes from a synthetic point of view. We have limited amount of building blocks available. So the isotope is generated in a nuclear reactor. And after a long cycle of irradiation of a nitrogen source, we have the first and unique building block available, which is barium carbonate. I would argue not the best synthetic building block to start with. And some of you are already smiling at that. Is it also quite expensive? So this is the cheapest starting material available. So usually the synthesis is performed step by step by step by step, increasing the complexity of the building block until we reach the final molecule of interest. So this is certainly a strategy that is working, but there is a number of drawbacks that come with that. In particular, is highly time consuming, is resource demanding. You just can't believe the cheapest starting material is that one. So all the rest is just increasing in a skyrocket way. And finally, heavy purification, heavy extraction will generate radioactive waste that will be difficult to treat. So in this context, we think that a late stage approach may be helpful in the field, and in particular, utilize this in the simplest starting materials and introduce them directly in the final molecule, ideally in one single step. So we have been working for quite a few years on this field, and one opportunity to perform late stage labeling is simply inspired by the work of our colleague with hydrogen. So is it possible to perform a carbon isotope exchange? So the concept is simple. Let's take a molecule, cleave selectively a carbon-carbon bond by any means, and replace it directly with a new carbon-14 bond. So our first attempt to perform a carbon isotope labeling was reported in 2018-19, and this work was done with my colleague at CA, Thibaut Quentin, who is not far away from here. And this is the work of the PhD thesis of Jeanne. So I got inspiration from copper catalyzed decarboxylation chemistry. There is a lot of literature over there, in particular the work of Gossen, but many others as well. So under thermal condition, we have a decarboxylation of unlabeled CO2 to generate an intermediate that, after optimization of the conditions, is able to trap against CO2, labeled CO2, to generate this carboxylate, which after workup will generate the corresponding acid. So the reaction, we start from a starting material, we end up with the same molecule, but we try to swap the carbon over there. So this was studied on a number of molecule for the scope, and was also applied to some molecule of interest, such probenecid and flumectin. So this is definitely my favorite example, because this molecule is a 4-quinolone antibiotic and was previously reported as a 10-step synthesis, 10-step radiosynthesis, so really something extremely heavy. So this showcases how a direct exchange may benefit the labeling technology. Well, once we started this work, there were some reports that came in the same period, and I can cite particularly the work that was independently published by Professor Baran and Professor Ruben Martin. So these two independent works start from this activated ester, and under a nickel catalysis, there is a reversible decarboxylation to obtain the corresponding carboxylic acid. Another work, remarkable work, was published by the group of Gauthier at Merck, US. So in this case, they used carbon monoxide, labeled carbon monoxide, starting from acid chloride in presence of palladium catalyst. And under this condition, they could, so in label directly carboxylic acid as well. More recently, we have reported independently at the same time with Professor Lundgren in Canada, a method-free approach to labeling. So in this case, the method is specific for phenylacetic carboxylate, and actually just under thermal condition in presence of labeled CO2 is possible to label those molecules. So the method is of interest because there are a number of compounds that are pharmaceutical with this structure. And for example, we could label ibuprofen, an analgesic molecule, but with good incorporation. But as you can see, the conditions are 160 degrees for 2 days. And it can be accelerated, but the temperature needs to increase at 190. So it's effective, but you may reckon that when you are handling a radioactive gas, you may try to avoid those conditions. So in this context, we thought that we could take advantage by the huge advances in photoredox decarboxylation chemistry, here just representative reviews, to assess a more mild way to perform the same reaction. Actually, so that we could have a decarboxylation of the starting material to obtain this radical that after reduction could actually be transformed again into carboxylic acid. So this work was tackled by my colleagues, and in particular these three gentlemen, so Victor, Alex, and Alexandre. And after optimization, they found that with the model substrate in presence of free equivalent of labeled CO2 for CZ IPN and non-phosphate base, it was possible to obtain the labeled molecule, as well as we have a byproduct of protodecarboxylation. So this is the very long story made short. And you reckon here that we work with carbon-13, so the stable isotope, of course, is quite evident of the reason why we do that. But we do that in the exactly same technical condition as we next go with carbon-14. So we studied the scope of the reaction, and here you can see some representative substrate of the transformation. So you can see here we have some good isotope enrichment. So this is the ratio between carbon-13 and carbon-12. We have overall, I would say, moderate to good enrichment. And the yields are, once again, they are moderate to good. I would say that in isotope labeling, one of the major concern is to get the final compound. So eventually, even if you have a low yield, an isolated yield, then if the molecule is enriched, is valuable as well. So in this context, we next look, of course, to the application of this technology to the radioactive isotope. So this was performed by my colleague at CEA, Antoine Salustreau. And as you can see here on the model substrate, we could have a 62% enrichment, which corresponds to 1,400 megabecquerel per millimole. And more importantly, you will recognize that ibuprofen now can be labeled in almost 40 degrees. The reaction is almost at 40 degrees. So with, again, a 50% enrichment will correspond to this molar activity, which is definitely in line for application in unmet studies. At this point, my PhD student, Alex Talbot, was curious. And he thought that this reaction could be useful to study the effects on the stoichiometry of CO2 in the outcome, basically. So we work on a specific manifold you can see here that allows to deliver a very precise amount of CO2, and then you can trap it in this in a reactor. This is a reaction with the forces dependent. You can see from the yellow color, and so you can really monitor the stoichiometry of the reaction. Actually, if you are familiar with carboxylation reactions, very often the amount of CO2 that is added to the reaction is not really taken into consideration because, of course, CO2 is not very expensive, the unlabeled one. So, but that for us is not, I mean, it's kind of problematic because we will be never able to reach those quantities as well as pressure. So this was interesting to monitor as a transformation. And what he found out is that, so here we studied on a model reaction. There are others as well where we studied. So here we monitor the formation of the labeled compounds as well as the formal protodecarboxylation byproduct. And you can see that below 1.5, 2 equivalents of CO2, the major product of the transformation is the toluene derivatives. And only after you have a sufficient amount of CO2, you can have the carboxylate as a major product. So next, he monitored the effect of equivalent of CO2 impacting the enrichment of the reaction. So again, the ratio between C12 and C13 in the transformation. And here in yellow, you have the theoretical values. And you can see that the experimental one follows quite closely the theoretical. We have seen that if we switch base and you use a carbonate, then we will see a much higher dilution. So the carbonate will impact the dilution of the compound. Well, Based on the literature and some of our results, we think that the mechanism of the transformation is this. So once the carboxylate is formed, there is a synchronous transfer between the photoxide photocatalyst to generate this radical 3 and the reduced photocatalyst. There will be spontaneous elimination of CO2 to form this carbon radical, which next will be reduced at the photocatalyst and will form this anion, which in the end will be sufficiently nucleophilic to react with CO2 and form the label starting material, the labeled product, I don't know how to call it. You have seen so far that basically all the isotope exchange technologies that have been recently reported, they tackle carboxylic acids. Well, carboxylic acids are great structural motif. We found those in pharmaceutical, but they account for 15 to 10%. So we wanted to go farther than that, and we thought about nitrile compounds because they are very representative in pharmaceutical. In addition, this is a very versatile building block in organic chemistry. So if you want to develop an isotope exchange with these nitrile motifs, then we believe that we need to tackle two different reactions. On one side, the activation on a carbon nitrile bond here, and next, the C-CN bond formation. So you all know very well that the second step, the cyanation, is a well-established transformation. There are plenty in the literature, and also for isotope labeling, this is something that is well utilized, starting from potassium cyanides and different other cyanide salts. On the other hand, if we want to tackle C-CN bond activation, this is quite challenging. Actually, just for we can see here that the CsP2-CN bond has a bond dissociation energy of 130 kilocal per mole. It's just for giving you some comparison. The C-BR bond is 97 and CH bond 112. So this is the basic of CH activation somehow. So nonetheless, in the literature, there are technologies that allows for the activation of this bond, and most of them, they deal with nickel. So we thought that this could be a way in order to assess a nitrile exchange. And once again, I was lucky to have very smart co-workers. So this was work that was particularly tackled by me, how Jeanne and Gianluca. And so what they found is that on this model substrate, the isotope exchange takes place using zinc cyanide as isotope source of 0.65 equivalents, 40% of nickel code, source stoichiometric amount of phosphine, and DMAP. So under those conditions, we have a very good yield, isolated yield of the compound, and the enrichment is 52%. So under those conditions, with 0.5 of zinc cyanide, the best incorporation that we can aim for is 56. So it was almost our best that we obtain. So next, we move on studying the substrate scope. So you can see here the scope of the transformation. We have electron-rich nitriles that can be tackled. We have as well electron-poor one, ketones, amides, aromatic motifs. We have noticed that the presence of fluorine is somehow tricky, so we need to reduce the time and the temperature of the transformation, and the enrichment is not so high, but still we could label that compound. In addition, we could also obtain this tocopherol derivative. Next, we look to heteroaryl nitriles because they are very representative in pharmaceuticals, and we were happy to see that on these scaffolds, we could obtain enrichment. So the enrichment is moderate to good, and the yields are usually more than 60%. So finally, we wanted to see if this methodology was working in real life for application for potential functionalized molecules. So here are the examples that we could label. And in particular, you can see we could label like fungicide, herbicides. This is letrozole is an aromatizing inhibitor. We have two nitrile motifs. We could obtain 43% of single isotope insertion and 10% of double insertion. We next could also label finerenone. So this is a compound that just received FDA approval. We have seen this on the Actualité Chimique last month. And so this is a molecule that was previously labeled starting from the bromide precursor. So you need to imagine that to do that, they had to develop all synthesis to reach the new synthesis to reach the bromide precursor. So at this point, we decided to look a little bit more into detail in the mechanism of the transformation. On stoichiometric experiment, we have seen that the oxidative addition took place and delivered the square planar nickel intermediate here that was isolated, and X-rays analysis were performed by Pierre Thuery at Aramis. And we have seen that once this intermediate is taken into the standard reaction condition, we can observe the formation of the desired label compound. On the other hand, to see isotope exchange on the intermediate, we have to lower down the temperature. And so in this case, we could observe that. So based on these experiments and on the literature, the mechanism, the suggested mechanism of the transformation is through an oxidative addition of a zero valent nickel to the nitrile to form this intermediate. Then we have switch of cyanide over there and reductive elimination. Of course, we were missing carbon-14, right? So this is at last, and we are very sensitive when we run this reaction. You can see here we bought zinc cyanide, was 100 milligrams. You can see that was not very cheap, and nonetheless we were happy to see that the molecule could be eventually labeled. So we were pleased by that, and you can see that at the same time very similar work came also from the group of Merck, from Merck US. So this somehow showcased that this is a field quite vibrant, but as well as chemistry that can be easily be reproduced as well. So this is a reliable protocols. Well, I come to the end of my presentation. I hope I gave you I could transmit some of my enthusiasm on the carbon labeling, and to see how this could really, like late stage technology could really help the development of carbon tracers, and in a really straightforward the synthesis of compound that previously are obtained over multi-step synthesis. At the end, I have the most important slide, of course. So the people that work on such projects. So here is the current group. I need to thank Frédéric, who is the leader of the department, who is a great mentor, Antoine Olivier for carbon-14 as well, Alex, Juan, Alexandre, and then the previous alumni of the group, Antonio, Gianluca, Michał, Victor, many others. And I would like to also acknowledge my collaborators. So from Sanofi, we work on the cyanide together, Jorg and Sebastian. My long-term collaborator is AstraZeneca, Chad Elmore. Of course, my colleagues at CA, particularly Thibault from Iramis CA, but as well I want to acknowledge Pierre because we work a lot with him. He's a great person. And then the current group, of course, the founding agency. None of these could have been done if they were not this agency, and you all for your kind attention.
So thank you very much, Davide, for this impressive and maybe expensive talk. Yes.
We do not do many reactions reporting.
Okay. So we have time for questions. Cyril?
Yes, thank you very much. It's a very nice presentation. Did you talk about your work on benzoic acid? In fact, did you test other type of substrate because you generate a benzoic radical that is very stabilized? Did you test other compounds, in fact, such as, for example, some proline derivatives?
Yeah, we were not successful with proline. Then Lundgren, he did a little bit of malonate also exchange on, he was a very similar scope. And then we, I think, yeah, I mean, phenylacetic acid are the best one. They can be trapped also in different ways. We are interested in the recarbonylation.
That's stabilized radical, but did you set some less stabilized radical?
Yeah.
Set some simple alkyl one?
No, those didn't work. I mean, only just simple one, they didn't work. Actually, it doesn't match with the potential for the photocatalyst.
Okay, thank you.
Thank you, David, for this really interesting presentation. I have just one basic question about the last slide, maybe I missed something. It works only with aromatics or with animals?
Thank you for your question. It works somehow less effectively on benzylic one. We are trying to work on that, and also on the aliphatics a little bit more challenging. So this is something that remains to be explored to get a successful exchange on those substrates.
Maybe I missed something, but in the cyanide exchange, you have only 1.3 equivalent of cyanide 13, and you should end up with a statistical mixture, or you have a
yeah.
The enrichment is quite high sometimes. So how do you explain that?
So statistical. So no, I didn't get entirely. So we have a 1.3 equivalents of cyanide. Yes. So 60 at equilibrium around 60%, 65%, and
but you should have a mixture of cyanide 12 and cyanide 13.
Yeah, 14, but it can.
Of cyanide 13,
yeah,
12, and you have only 1.3 equivalent of cyanide 13. So you will have a statistical mixture.
Yes.
Of enrichment.
Yes. This is exactly what we can have actually in this case. So one of if everything works fine and we have no substrate degradation, because then it's complicated, but we have one equivalent of unlabeled starting material, so one equivalent of 12 CN, and then here 0.5 is 2, the ratio is 2. Well, I didn't do anything, I swear, and so 1.3 equivalent. So over there is 55. So this is the best we can get. Often we get less because probably it doesn't react entirely with the substrate, but we cannot achieve more than that in terms of enrichment.
On your table, I confused with the yield.
Yeah. That is probably it's my fault. I didn't precisely, but yield is isolated compound as all the reaction, and then the one in green or blue is the enrichment. So that is the ratio of the two isotopes that can be determined, for example, by mass as well.
Okay.
Thank you, David, for the most expensive work of the day. For the nitrile exchange, can you escape the statistical distribution? First, taking your nitrile and doing an exchange with an X, maybe not an halide, but an acetate. Something that would be a bit more up here, but just force it with a massive amount of acetate. And so that afterwards you can add the label cyanide and have a 100% conversion.
That is that's a good idea. We treat something, but not extensively. But that would be good, because for some application we need higher enrichment, and also that would solubilize. Yeah, ideally it would be best to do without isolating it to the nickel 2 complex, but because that could be doable. But yes, that is a good point. Yeah, definitely a good point.
Thank you.
And the last one.
Thank you then for this very nice talk.
Thank you very much.
Did you try other catalysts for the benzonitrile?
We are working on that. We tried. We explored a lot of those. I mean, I didn't show, but we tried different nickel sources. We are still working on that to get something which is more, because that is nickel 0. Pharmaceutical companies, they don't, I mean, at least in the labeling department, they don't like too much glove box and so far. So we are working with some alternative, which is much easier to handle. And then we are also trying to explore for to eventually go further. There is some opportunity eventually, yeah, there, sure.
Yeah,
I have seen some literature from not far away from us on that. It's in my PC.
Thank you.
Okay, so we will stop here the discussion.
Thank you very much.
Conclude. So Davide. So I will give you the award, this Jean-Pierre Sauvage Award. So this is awarded by the DCO divisions, past and present. So we are happy to award this Jean-Pierre Sauvage Prize. And I have to precise that it is an award which is given to people who have been hired less than 8 years from today. So thank you very much.
Thank you very much. Thank you very much. I deeply appreciate and I dedicate this to all my coworkers and mentors. Thank you.
Now we have a coffee break. It would be very nice to be back here at 35. Catch back some time. Don't forget your anti-COVID label to come back in the room.
À gauche.
Okay, so we will restart. It's the last session of today, so it has been already a very nice day full of science, and we still have 2 lectures to come. One is the normal communication, so it's one of these possibilities that we're offering every time that we do a special day, so at the fall or at the spring. So as Frédéric said before, don't hesitate to postulate to this kind of things, to apply, because it's always a great pleasure to see some people that we don't see all the time. And so no, but that's right, because we always see people coming from abroad, but finally it's usual not to know as well the French community. And so it's always a good opportunity, and it's always very nice to see all these people. So we will start with Jennifer Molloy, who's coming from Grenoble, and she will do one of these oral communication. So the floor is yours.
Thank you very much. Thank you for the opportunity to talk to you today about my project. So I'm Jennifer Molloy. I'm chargée de recherche CNRS in the Département de Chimie Moléculaire in Grenoble. And so I'm going to talk to you today about the design and synthesis of a multi-topic pro-radical probe for the detection of oxidative stress. So first of all, what is oxidative stress? So what's important to know is that in our tissues and cells, we have what's called a cellular redox homeostasis. So what's that? I think most people know it's a perfect balance between the generation of reactive oxygen species and the generation of antioxidants, which counter these reactive oxygen species. So we have always this specific equilibrium of 2 types of species. What happens when we have oxidative stress? We have a disruption of this cellular redox homeostasis, and so we have an increase in the production of the reactive oxygen species, which the antioxidants can't handle. So we have an overproduction of these kind of species. So what happens when we have this overproduction of ROS species? Well, we have an oxidative stress, which can cause lots of different problems. So for example, cardiac diseases, diabetes, neurodegenerative diseases, and cancers. So in particular, elevated concentrations of ROS have been found in many dangerous diseases, particularly related to neurological disorders, gastric problems, and heart problems. So more specifically, what is this oxidative stress? It's the overproduction of reactive oxygen species, which is any kind of reactive oxygen generated species from O2. So for example, the most common and the most known maybe are the hydroxyl radical, the peroxides. And so these can be very dangerous and toxic in our cells. So if we could generate a redox switch, which could allow an indication of tissue health or cell health, this could aid in the diagnosis and treatment of these illnesses before they become a very dangerous. So what we're going to try to do is to monitor the redox state or monitor the production of specific ROS in order to try to aid in the diagnostic process. So how could we develop a redox switch for these kind of species? Well, what we want to try to do is develop a redox switch that has an on-off effect. So like a light switch where we have in one condition it's off and in one condition it's on. So for example, one of the approaches we take is to use a reporter and a detector. So for example, a metal complex where we can excite the chromophoric ligand attached to the metal, and then transfer occurs to the metal ion and a luminescent signal. Upon oxidation of this complex with a ROS or a simple oxidant, we can show that this energy transfer process is switched off, and so our luminescent response is switched off. So we have this on-off effect. What we want to try to do, because we work a lot with lanthanides in our group, so we wanted to see if we could use lanthanides in these type of redox switches. Why in particular the lanthanides? They have fascinating luminescent properties, so they've long-lived lifetimes and specific fine line emissions, so very good in terms of detection. We're also interested in the lanthanides because they have also fascinating magnetic properties. And so one of the things with redox switches is we could maybe couple these magnetic properties with redox signals. One of the big problems with that is that lanthanides inherently can't be used as indicators of redox activity because they have a tendency to exist in their +3 oxidation states. So the lanthanide itself will not be very redox active. So how do we overcome this? Well, we are focused on the use of redox active ligands, which in turn can be used to communicate with the lanthanide, and the lanthanide will give a response. So for example, in this idea, we have the detector, which is a ligand with a redox active function, and the lanthanide, which will give us our response. So our project focuses really on the development of these redox active ligands, which will allow us to concentrate the redox activity on the ligand, and the lanthanide will just be there as the reporter. So one of the projects that we have already carried out a few years ago is the development of tripodal complexes. So based on a tripodal structure with 3 phenolate ligands, with 3 phenolate moieties on our ligand. And the interesting thing about our phenolates is they can be redox active and form the phenoxyl radical. So we studied a series of lanthanide complexes with these tripodal ligands. So we did all of the complexes of the lanthanide series pretty much. And we were able to crystallize all of these complexes. And the electrochemistry showed us that we had 3 distinct oxidation waves, which corresponded to the oxidation of each of these phenolates into the phenoxyl radical. So we could show that the redox activity was centered on the ligand, and it allowed the isolation of the oxidized species. The next point was to try to see if this redox activity could give us a response of our lanthanide ion. So what we were able to show was that our lanthanide luminescence was very sensitive to the redox state. So we could have, upon addition of an oxidant to oxidize the phenolate to the phenoxyl moiety, we could have almost a 90% quenching of the luminescent spectrum of our lanthanide. And so we had our lanthanide luminescence, which was very sensitive to the redox state, and we could have reversible conversion between the 2 redox states. So this was a proof of principle to show that our redox activity has a dramatic effect on the properties of our complex. Then what we needed to do, because these oxidation potentials were quite high for any kind of biological application, so the idea was to try to use new redox functions and more soluble lanthanide complexes. So I decided just to talk to you today about one part of this project. So this is Richard Barry's work, who's a PhD student who will be finishing soon his thesis with me. And he tried to do bimodal detection of hydroxyl radicals with the spin trap system. So he designed this ligand based on a macrocyclic cyclin ligand, complex 2-lanthanide ion, and a redox active arm, which is this is the pro-radical, so the aminohydroxylamine. So the scaffold was chosen because it really chelates quite well the lanthanide ion, and it provides us water solubility. The redox active function with the pyridine unit attached allows us to excite the lanthanide for luminescence because it acts as an antenna. And this moiety is redox non-innocent, and so we can follow also the activity by EPR. So first, the synthesis had been already carried out by a postdoc in our group before Richard had started his thesis. And so he used this synthetic pathway, but there were a few problems with this synthetic pathway. The first was the stability of this amine that we used to form this intermediate. So this wasn't very stable, and it required immediate utilization. If not, it degraded almost immediately. And we couldn't scale up this reaction. So it wasn't very practical. And this last step, which was the oxidation of this diamine into either the nitronal nitroxide or the amino nitroxide, led all the time to mixed products. We couldn't, and it was very difficult to isolate either one of these products, despite them being very colored and so easy to see. So Richard, his first job really during his thesis was to try to optimize the synthesis. So he decided to optimize the synthesis of the pyridine by starting with the dialcohol. And so first of all, oxidizing to form the aldehyde, and then to chlorinate the other arm and to have this intermediate here. And then instead of starting with the amine intermediate and directly reacting the amine with this aldehyde, he decided to start from the dinitro compound to form the dihydroxylamine, the bisohydroxylamine, and then to form the sulfate salt. And this sulfate salt was particularly stable, and so could be kept in the lab for quite a long time. So it was much more practical for synthetic reasons. And then he could react this bisohydroxylamine with the aldehyde to form this intermediate. So this intermediate allowed us to directly perform the oxidation on the bisohydroxylamine to form the nitronal nitroxide arm. And in this case, we had only formation of this nitronal nitroxide. So we then looked at the characterization of this system. So we had the EPR. So we looked at the EPR to make sure that it was in fact the nitronal nitroxide that we were looking at, and it had the distinctive fine-blind signal of 2 equivalent nitrogen atoms, which are significant of a nitronal nitroxide species. And Richard was also able to get a crystal structure of this arm. So the next step, this was the redox active arm that we wanted to use. We needed to functionalize it onto the macrocycle. And so we started with the tri-substituted cyclin macrocycle and did as a nucleophilic substitution to add our redox active arm. The redox active arm was added in the form of a nitronal nitroxide, but upon deprotection of the terp-butyl groups, we found that we had no longer this was a bright violet color. And when we did the deprotection, we recovered a yellow product. So we were wondering what this yellow product was. And when we looked at the NMR, this is just the NMR spectrum of the ligand, where we see the characteristic pyridine protons and the big mass that is significant of the cyclin macrocycle. When we looked though at the HMBC, we could try to look and see what characteristic features we could see. And we could see that we had peaks at characteristic of the hydroxylamine and characteristic of an amine. So this suggested that we had this structure. So during the deprotection process, we have conversion of the nitronal nitroxide into an aminohydroxylamine. So we carried out complexation of this ligand with europium and ytterbium to form this complex. Richard purified these complexes using Cepheid chromatography and characterized by IR and HRMS. We could get crystals of this complex, which showed that in the solid state it could be isolated in its nitrone form. And all of these complexes were 9-coordinate complexes. So the next step was to look at the potential interaction with reactive oxygen species. So the first thing we did was to look at its interaction with an oxidant. So we looked first at the luminescent response. So we carried out the excitation of our complex at 290 nanometers, which showed us a distinct emission for both the europium and the ytterbium species. The europium indicates a CN symmetry because of the presence of the 7F2 band, and we could determine the lifetimes, which allowed us to calculate the number of water molecules on the complex, and it showed 0.5 water molecules. This might seem strange, but it could be because we have either coordination of the hydroxylamine or because we have a hydrogen bonding network of a water molecule between the different complexes. So we showed that we could sensitize the lanthanide emission using our redox active unit. The next thing to do was to add an oxidant and see what effect this oxidant would have on the properties of our complex. So the presence of an oxidant, we used a simple oxidation using cerium ammonium nitrate, or we also used a periodate. And we showed in both cases that we have a 90% quenching of the luminescent signal for both europium and ytterbium. So our luminescence was sensitive to the presence of an oxidant. So we did the same check in EPR to make sure we had a change upon oxidation. So the europium complex shows no inherent EPR signal for the europium ion, and the reduced species is EPR silent. So in the beginning, we have a silent EPR spectrum, and upon oxidation, we have the 7-line EPR signal, which is characteristic of an amino nitroxide. So we could show that we could follow the formation of the radical species by both luminescence and EPR. The next step was to see if we could react our complex with ROS. So we chose the hydroxyl radical as the most reactive and toxic reactive oxygen species. And we used a typical hydroxyl spin trap experiment design. So in order to generate the hydroxyl radical, which is missing its, we used classical Fenton reaction conditions. So we used an iron sulfate salt in the presence of peroxide to generate our hydroxyl radicals, and we monitored the response by EPR and by luminescence. So first of all, the luminescence results. So when we added our complex into the Fenton reaction conditions, we expected the formation of the amino nitroxide. So the oxidation of the amino hydroxylamine into the amino nitroxide. So we see, compared to what I showed you just before, the luminescence spectrum, which decreased by more than 90%, here we see practically nothing, very, very small decrease. So we weren't quite sure what this meant, but we could show that we had a small effect of the ROS species on the luminescence spectra, but not a large enough effect for detection. So this very weak luminescent decrease wasn't great news, but when we looked at the EPR spectra, we could show that in the same conditions, the red spectrum is the complex for both the europium on the left and the ytterbium on the right. So the complex shows that they're EPR silent before addition of the ROS, of the hydroxyl radical. What we observed after addition of the complex into the Fenton conditions was the appearance of the amino nitroxide distinctive band in the EPR. What was interesting about the EPR of these species was over hours and days, we could see that the EPR spectrum evolved and formed a second species. So the amino nitroxide wasn't very stable in these conditions, and it evolved further to form the nitronal nitroxide. We confirmed that it was the nitronal nitroxide that was formed in this experiment because we could isolate this compound, and using mass spectrometry, we could confirm that it was the nitronal nitroxide. We simulated this. This spectra was quite significant of a nitronal nitroxide, but we wanted to confirm that. So we did simulation spectra for each of the different species formed using EasySpin software. So for the ytterbium, this was the amino nitroxide experimentally, and this was the simulation spectra. So we see that it was really the amino nitroxide that we formed at the beginning of the experiment. And after days or hours, depending on the complex, we could see that this spectrum of what we assumed was the nitronal nitroxide, the simulated spectra confirms this hypothesis. So when we integrated the EPR signal, the deconvolution signal for each of these spectra, we could see the decrease of the amino nitroxide signal over time and an increase of the nitronal nitroxide. So the nitronal nitroxide was really, the amino nitroxide was converting into the nitronal nitroxide complex. The yield of the reaction, when we calculated the yield of these reactions, it was very low. It was about 1%. And so this is in accordance with our luminescence, where we saw a very, very small decrease in the luminescence spectrum. However, in comparison to classic spin-trap based on organic molecules, such as, for example, the DMPO, our complexes are actually quite interesting because the radical that forms with the DMPO is very unstable and degrades in the space of less than an hour. Whereas our systems, even after 16 to 20 days, the radical was still very stable and the intensity had not decreased. So just to conclude, we were able to synthesize and characterize a redox non-innocent ligand with an alpha aminohydroxylamine arm. We were able to obtain their lanthanide complexes and characterize them in particular using EPR and electrochemistry. We could show that we had an evolution from an unstable amino nitroxide to a stable nitronal nitroxide radical in the presence of hydroxyl radicals. And we could use bimodal detection using EPR and luminescence. And just to finish, I want to acknowledge the people that worked on this project with me. So Richard Barry, who's the thesis student who worked on most of this project, Damien Mouchel-Dilaguerrier, who worked also with him on the optimization of the synthesis, and Professor Fabrice Thomas in my team, who does a lot of the EPR experiments, and the ANR and KAGAN for funding. And thank you for your attention.
Thank you very much, Jennifer, for this very nice talk about your lanthanides and luminescence. It's very interesting. So I'm pretty sure that there is several questions from the audience. Don't be shy.
Very nice work, Jennifer. I was wondering, you have shown a lot of EPR, but you didn't show any magnetic properties because you have your radical interacting with your lanthanide. Maybe it's interesting.
We have done it. We don't want to show it because maybe we're going to try to patent it. So to patent the work with the other lanthanide complexes. That's why it's not sure yet, but we're not presenting.
Because your ligand has several sites, so you could make a multi-radical
Yeah, absolutely. And it's one of the things, not with this particular system yet, but we have done, for example, bis substituted complexes with two different redox units or the same redox unit on two different sites. We have done this. I didn't present it today, but we have.
Are there any other questions? Maybe in the chat now? Okay. Okay, so thank you very much once again.